so we are recording the session as the meeting asked us, okay? I will just share here for you to really have in mind, okay, what is the schedule of our section of white dwarfs. So here you see the program is exactly the same I sent for you before, so no any changes, okay? So first begins Quantai, okay, Boskayev, after Bani Brata, dead at 7:05 in this test time. Here, Nicholas and Sarah, Well, Rafael, and at the end, Sylvia. Last says already the speakers now, only of.
Oi, tive problema com o som aqui.
Okay, so I'm showing here that.
Yeah, I'll be coming back soon. I'll just try to check other session where I'm going to speak around
don't worry.
6 o'clock, whether everything goes well.
Quantai is on, Quantai is here or not? Because I'm not seeing him now, so.
Not here, no.
Not here yet, yeah, that's the problem. That will maybe need to change these things here. Take some off here. So, okay, so it's exactly more what I sent before, only for you to know, okay? That of course, the idea, as I said, is you have 15 minutes and after +5 for questions. No, of course, 15 if you pass a little bit, but try to be on time because the session is ending after 15 minutes of our last after 7:30 on CEST. So we cannot really stay longer speaking each. So I ask you, please, to really try to be in your time, really, with some effort, okay? I will say something when you arrive more or less at 13 minutes, I will say, or 12 minutes, I will say 3 minutes, okay? If it's in some sense to help, okay? Or if not, when it's 15 minutes, I will really say something, okay? So,
okay, perfect.
So I think now it's everything okay. Only Quantai, let's stop sharing now. And let's wait if Quantai comes here. All right. Sorry.
Rafael, you can test your presentation?
What?
Rafael.
Sorry?
Rafael.
Yes.
If you want, you can test now. Yeah.
Can I test mine too?
Yeah, of course.
Yeah.
Okay, I'm going to test.
Sylvia, okay, perfect, Sylvia.
Okay, this is mine. It's okay?
Yes.
We
Yeah,
can
okay.
see.
It's perfect, Rafael.
Hello, this is Devabrata. Let me test my slide.
Quantai is here.
Nice to see you.
Hello, this is Ziel.
Nice to see you. Quantai. I was
Hello,
worried.
Professor, how are you?
Okay, so nice to see you. Be welcome. Just see if everything is on.
Yeah.
And
Okay. So how many participants do we have?
I think usually I saw that they are usually, where is this?
My slide visible, right?
Yes, it's all.
Okay.
Yes, there. It's okay. Your slides.
Okay.
It's fine.
Okay.
Yeah.
Oh, yeah, I hear a whistle.
So I think it's 11:25 still. No. Okay, for me. Sorry. 4:25 in the SAS time. So we have still 5 minutes.
Yeah, for me it's 8:23 p.m.
Oh, sorry. What is the time you said?
8:23 p.m. is evening for us.
Yeah, 8:30 evening. Yeah, is what I suppose. So from Brazil, you are the 9 hours in advance. 9 hours.
Yeah, okay.
We are almost at noon here, half an hour for noon.
Good.
Hi, can you see a sound? Or is my only to me?
We also hear this whistle.
Yeah.
I don't
I
know.
hear it too.
And my sound is not very good, really. So I have problems, but I think the others are okay.
Mm-hmm.
You can drop a little bit your sound, your volume.
I think during the presentation, only speaker should switch on the microphone and then should be fine.
Yes.
Yeah, so
I just changed my laptop. Can you hear me properly now?
Excuse me?
Are you able to hear me properly? Other session where I'm supposed to speak, they are not able to hear from this laptop where I'm now currently, logged in. So I switched other session.
I'm not understanding, Fanny, very well.
Okay.
Speak slow.
Are you able to hear me properly?
Yes, everything properly. Yes.
Everything's all right, right? Okay.
Yeah, but the first one, the first speaker is Quantai. Okay.
I know.
Second one, no? Yeah.
I know.
So,
The reason I'm asking, other session where I'm supposed to speak also, they are having problem when I was trying to present myself with this laptop. So I changed the laptop. So I thought,
yeah, that's fine.
but it's all right. Okay.
And so, as Quantai already said, now during the presentation, we are asked to have our microphones off, okay, and also our cameras. Only remains Quantai speaking and for help connection, please. So Quantai, so we are now almost at the time. So if you want, you can begin sharing your presentation. See, I think everything is fine. Yeah. So start again. So Quantai Boshkaev is from Kazakhstan, of Farabi Kazakh National University. Is a specialist in really rotating white dwarfs and relativistic calculation, structure, and finite temperature effects, and several works on that. So, Quantai, be free. If you want to begin, we can begin.
Okay, Professor, thank you very much for this introduction. First of all, I would like to thank all the organizers of the conference for inviting me to give my talk. And the topic that I'm going to present is called static and rotating white dwarfs at finite temperatures. Okay. So this is the outline of my presentation. And first, I will speak about motivation and objective. Second, I will briefly describe the equation of state that we use in our research. Then I will show you also the structure equations from where we started our computations. And of course, I'll present main results and in the end, summarize our conclusion. So we all know that white dwarfs are considered to be the most abundant stellar remnants among compact objects. And of course, we know that white dwarfs are formed when main sequence stars with mass between 8.5 and 10.6 solar mass evolve. So at the end of their evolution, they will end up as white dwarfs. And it's well known that if the mass of a white dwarf exceeds the well-known Chandrasekhar mass limit, depending on the nuclear composition, white dwarf can explode as type 1a supernova or collapse into neutron star. So in this presentation, we consider separately and together the effects of finite temperature, angular velocity, rotation, and general relativity on the structure of white dwarf stars. We show that combined contribution of the effects is not always straightforward, as one may think. So we start with Chandrasekhar equation of state. It is well known in the literature, and it is considered to be the simplest one, and at the same time, it is the basic one. All other equations of state for white dwarf matter, they make some changes, some contributions in the structure of white dwarfs, but the main contribution comes from this equation of state. So according to Chandrasekhar, the energy density comes from the energy density of nuclei, and the pressure comes from the degenerate pressure of electrons. And all these quantities are very well known. So Ne is the electron number density, and mu is the ratio between atomic number and the proton number in nuclei. So we adopted two cases when M equals 2 for helium, carbon, oxygen, and so on. And we also adopted a second case when mu equals 2.15 for iron. This is just for comparison. And the most general definition of the electron number density comes from the Fermi-Dirac statistics. So we know this expression, and when we take into account the effects of finite temperature, we can write it in this form, where f, this function, is called the relativistic Fermi-Dirac integral. And all these quantities are related to the temperature, so they are called the degeneracy parameters. And the pressure of electrons in the case of finite temperatures will have this form. And of course, when we consider zero temperatures, we will obtain the well-known Chandrasekhar equation of state for cold white dwarfs. And we also made the following assumption. We considered only isothermal cores, just neglecting the effects of atmosphere, because the contribution of atmosphere to the whole structure of the white dwarf is negligible. So in order to find the relationship between the core temperature and the observed surface temperature, one can use the so-called Koester relation. So where G is the surface gravity, or just free fall acceleration. And we also show the structure equations. These are expressions in Newtonian gravity. Of course, in general relativity, one should use Tolman-Oppenheimer-Volkoff equation. And in general relativity, the angular velocity will have a more complex form, because it should include frame dragging effect, the quadrupolar deformation of the star, and in Newtonian case, it accepts very simple form. So taking into account the Chandrasekhar equation of state and the structure equations, we can calculate the main parameters of rotating white dwarfs at finite temperatures, including the effects of general relativity. And I should just mention, we use Hartle formalism because it is well established for compact objects, including neutron stars, quark stars, and here we use it for white dwarfs. And we use it both in general relativity and Newtonian gravity. So here we show mass central density relation for static and rotating white dwarfs at finite temperature. So all dashed curves indicate rotating white dwarfs, and all solid curves indicate static white dwarfs. And as you can see, in static case for larger densities, all curves for the mass converge, so they are almost identical to the degenerate case. But in rotating case, we see that they are different from each other. And we see that cold white dwarfs will be more massive than hot white dwarfs for fixed central density. And here we have the same plot, but for smaller ranges. And we see that in static case, the effects of temperatures are important only at smaller densities. At large densities, the effects of finite temperatures can be negligible. But for rotating case, no, we should take into account the effects of finite temperature. And on the left panel, we see equatorial radius versus central density. Sorry? Okay, I'll continue.
Continue.
So, yeah, we see that for fixed density, cold white dwarfs are always smaller in size. So here, black curve indicates cold white dwarf, red and blue indicate hot white dwarf. So hot white dwarfs will be always larger in size when central density is fixed. So in this plot, we have angular velocity versus central density. So as you can see, for fixed central density, angular velocity of cold white dwarfs is always larger than angular
I'm sorry,
velocity.
Kuntai. I'm
Yes.
sorry. Manuel, turn off the audio of the participants, please.
Yeah. Okay.
Sorry, what am I supposed to do?
No, that's fine. I just mute here. Some participant was with microphone on. Sorry.
Ah, okay. Okay.
Sorry.
Yeah, okay, no problem. So we see that, in other words, cold white dwarfs rotate faster than hot white dwarfs. So in all the range of the density, we see that cold white dwarfs always rotate faster than hot white dwarfs. So in this plot, we have two diagrams, mass versus angular velocity, and equatorial radius versus angular velocity. And for fixed angular velocity, especially for small values, we see that the mass of hot white dwarfs is larger than cold ones. But as soon as we increase the value of the angular velocity, we see that at certain point, this behavior is reversed. So here, at larger angular velocities, we see again opposite picture. So cold white dwarfs possess larger mass. And in the case of equatorial radius, we see that at larger angular velocities, they converge, so they become unique. But for small values of the angular velocity, we see that hot white dwarfs larger in size. So, and finally, we constructed also mass radius relation, because these are the most important relations that we observe. And for mu equal 2 case, we have this plot diagram. And for mu equals to 0.15 for iron, we have this plot. And we stopped our computations at critical densities corresponding to the inverse beta decay density. For iron, it is around 10 to the power of 9. And here it's around, for, if you take into account carbon, it is around 10 to the power of 10 gram per centimeter cube. So as we can see, the effects observed for static white dwarfs also translate to the rotating case. And the only difference appear when we reach, when we nearby the maximum mass limit. So this part I will show you in the next slide. So for iron white dwarfs, the picture is similar. The only difference that for iron we have smaller critical density, and correspondingly iron white dwarfs usually are larger in size but smaller in mass. But the rest is the same. I mean, the whole behavior for small masses, the whole behavior is the same. So in this plot, we show that the contribution of general relativity becomes important again close to the Chandrasekhar mass limit. So the difference between Newtonian gravity and general relativity is larger than 1% for static case, and is around is again larger than 1% also for rotating case. And for iron white dwarfs, we see that the effects of general relativity is even smaller than 1%. So one can neglect general relativity for iron white dwarfs. And we know that general relativity plays a crucial role when we investigate the stability of white dwarfs against perturbations. So in the table here we show for fixed central densities the numerical values of the masses. For example, this is for helium, carbon, oxygen white dwarfs, and this is for iron white dwarfs. We fix these densities and calculate the mass for different temperatures for static and rotating cases. And we see that for static cases, the masses will be the same irrespective of the value of the temperature. But when we rotate white dwarfs, the values of the mass are different. And of course, cold white dwarfs are more massive than hot white dwarfs. And the same is true also for iron white dwarfs. And in the table, in table 2.
Okay.
Yes.
Only between the brackets are the Newtonian values, yeah?
Okay, so these values in Newtonian gravity, and in parentheses, the values are in general relativity, in GR.
Okay.
So the difference is less than 1% here, at least for this value. And here, is larger than 1%. So in parentheses, the values are calculated in general relativity, and this is in Newtonian gravity. In table 2, instead we fixed the value of the radius, and we see that for rotating case, again, cold white dwarfs will possess larger mass with respect to the hot white dwarfs. So the explanation is not so simple. One can imagine that since hot white dwarfs are more fluffy, larger in size, and correspondingly, if they have the same mass as static ones, they cannot rotate faster. So if they cannot rotate faster, it means that their central density should be larger than for static case or for cold white dwarfs. So in the conclusion, I would like just to stress that the results obtained in this work presentation can be applied to observed white dwarfs in order to theoretically estimate their core temperatures, mass, radius. Also can be applied to soft gamma repeaters, anomalous X-ray pulsars within the white dwarf model of magnetars to calculate all the parameters such as the mass, radius, moment of inertia, magnetic field, etc. Also, results can be applied to fast rotating white dwarfs, such as this source with spin period of 29.6 seconds, and this source, though this source sometimes considered to be white dwarf in the works of Merighetti, but up to now the nature of the source is still unknown. Okay, anyway, we can investigate the source as a white dwarf because its period allows us to consider it as a white dwarf. And of course, we can extend our computations, our research in this direction, including more realistic equation of state for white dwarfs. We should take into account nuclear composition properly, Thomas Fermi corrections, Coulomb interaction, magnetic field, anisotropy in the pressure, and so on. So the same studies can be carried out within the modified or extended theories of gravity, where we have contribution from the parameters of these theories. So details of this presentation can be found here on archive, and work is still in progress. So thank you for your attention.
Thank you very much, Wantai. You have still some minutes for some question. Someone wants to make any question, please open the microphone and make the question.
I wanted to make one, but Banbrata.
Okay, Bani Brata, make the question.
Yeah, I have a couple of related questions. Number one,
Speak slow, please.
Okay, sorry. If I understand correctly, you had introduced temperature effect in the equation of state. But then temperature gradient also should be considered, at least in the envelope region. If core is assumed to be isothermal, all right, but envelope. Did you check that? Number one. And number two, if it is rotating, then white dwarf, of course, depends on the rotation rate. White dwarf might be not spherical, oblate. I understand, if I understand correctly, you did not consider oblateness of the white dwarf. Can you make some comment? Or because I believe both the effects might increase the result or might change the result as well. That's what I'm asking.
I'm sorry, I'm afraid I couldn't understand your question.
I think he said, if I understood, he said that for not so massive white dwarfs, where you've seen the temperature effects are important. I think he asked about some that the envelope is going to be important.
I mean to say temperature gradient in the, apart from dPdr, dmdr equations, you also should consider dTdr equation where you have finite temperature calculation.
Well,
I don't understand, Bani Brata. What equation, d what?
dTdr, derivative of temperature.
No, in our case, we have only isothermal temperature. So it is simplified model. We don't have temperature gradient. We assume that the temperature in the core of a white dwarf is constant everywhere. And yes, of course, we know that the contribution of atmosphere or envelope can be important for small mass white dwarfs, but for massive white dwarfs, of course, we can neglect them. So I don't know if I understood your question correctly, but
Maybe
it's
my
hard
voice is fluctuating. I'll change my laptop. Maybe you have still 2 minutes.
Yes, okay.
Others go ahead.
Okay, yeah. So, Sylvia, one more question you want to
Yes.
make?
Yes. In the equation of state, you have the Fermi-Dirac integrals.
yes,
So how do you solve them?
only numerically.
Well,
We
you know
solve
the
them
method.
only numerically because analytic solution for this kind of integral, it's not obtained. We give different values for eta, we give different values for beta, we fix temperature, and then there is a whole table for eta and beta, and then we calculate this integral numerically. And for each value of beta and eta, we construct the dependence of this electron number density. And once we know the number density, we can calculate the pressure, and we can calculate also the energy density of
But I'm
white.
asking the method you use to integrate numerically. So, you know, you use a subroutine or something like that.
Well, we don't go into details. We just use Maple or Mathematica, and
Okay,
we
okay,
integrate it numerically. Yeah.
okay.
Okay.
Of
Thank you.
course, we can choose the precision.
Okay, so let's thank you.
Manuel, yeah, we can move to the next talk.
Yes, I'm going to move, yeah. So let's thank you. Quanta, if you want, you can unmute your font. And so let's
Okay. Thank you. So
Okay,
I
so
should
let's next speaker, Manibrata, please. So stop. Yes, okay. So stop sharing, please. One
Okay, I
time.
stop.
Thank
Yeah, I
you
stop.
very much.
Mhm. Thank you, thank you.
Manibrata.
Yes, yes. I have changed laptops in last couple of minutes.
That's perfect.
I leave from other laptop, otherwise it will be.
Try to speak slow because your sound is hard to understand.
Hello.
Can you start, Bunny?
It was okay.
Yeah, yeah. Can you hear
It was
me?
okay before. Yeah. Before was okay in full screen.
Okay,
Yeah,
is it all right?
that's fine.
Okay. I'll start my stopwatch so that I'll be able to finish on time. And I'll take my pointer. All right. So thank you. I would like to thank the organizer of the session for giving me this opportunity by inviting me for this session, where I'll be talking about in next few minutes, next 15 minutes, just a minute. I have some problem here. Last moment I changed my laptop. All right. Okay.
Yeah.
So
In fact, now it's not in full screen, but that's fine. You can see.
okay. Okay. Now it is full screen, right?
Now it's full screen. Okay, good.
Okay. Thank you. Sorry. Yeah. Thanks very much for inviting me to give a talk in this session, which will be current status of highly magnetized white dwarf and its implication. What we started about 10 years back, and then we have developed the model one by one by introducing new and new physics that I'll highlight, and the problems, underlying problems also I'll try to highlight. This result I'm going to present is kind of output of intercontinental collaborations
here names of my collaborators are, just a minute again, I lost my pointer. Yes. Name of my collaborators. Basically, violet color corresponds to my current or past students or postdocs, and green corresponds to some of my colleagues from other institutes all over the world. So majority of the new work what I'm going to present here is done by Mukul Bhattacharya, who is in now Virginia Tech. Unfortunately, he is now suffering from COVID. He's in hospital. I wish him very early recovery. All right. So as I said, well, before that, since last 15 years or so, at least a dozen type 1a supernovae observed, which are quite peculiar in terms of their light curve shape and their oval luminosity, and also low ejecta velocity. And they argue for the existence of super Chandrasekhar progenitor white dwarfs. And since last 10 years or so, we have been enlightening the underlying reason by introducing magnetic field in the white dwarf we call B white dwarf, leading to new super Chandrasekhar mass limit. There are other consequences, white dwarf pulsars, gravitational radiation, I'll touch upon very briefly. Also SGR-XP, our session chairman also work on this. And immediately that brought super Chandrasekhar white dwarf in the limelight. Many groups joined working in this field. Many of them actually went beyond magnetic field based idea, even including our group. Like previous speaker told, modified gravity was introduced, matter encountering non-commutative physics at high density was introduced, having ungravity effect, net charge, Monday's talk, also Czech group, having many variant magnetic fields, for example, anisotropic field effect, see the next talk. All in principle could give rise to massive white dwarfs, but for the present talk, I'll concentrate on magnetic field based idea. And all of them in principle lead the mass radius relation varying from that of Chandrasekhar. It could be also shape-wise prolate or oblate spheroid, but problem is there is no direct detection. That I'll try to enlighten what's the reason and how it could be possible. All right. So observation side at a glance. So peak luminosity of the type 1 supernova, if you plot as a function of 15 days decay from the peak, you see these guys, conventional type 1 supernova, they follow Phillips law. These guys are super Chandra candidate with very high luminosity, nickel mass violates Kokolov limit. So they don't follow Phillips law. Those are the target. And they are there. Observationally, you cannot deny. They are there. You have to prove. I mean, you can say it is not there, various effects, but you have to explain those. I mean, you cannot say, you can say that super Chandra is not there, but you have to prove them. So how strong field could be if I am trying to argue magnetic field based idea? So Cambridge Star's group, for example, Cambridge Star's code, for example, argue that at the end of main sequence star, field could be toroidally dominated and could be all the way 10 to the power 7 to 8 Gauss in the central region. And then it decays towards surface with low field. And if such a star, as further being simulated by Star's code by Cambridge, that's our latest work, this paper, collapses to form a white dwarf of say 1 million kilometer size from the, initial star is 10 to the power 8 Gauss and radius 1 million kilometer. If that star collapses to a white dwarf of 1,000 kilometer size, field at the center no less than 10 to the power 14 Gauss. That is our kind of physical field and central field, example field we consider throughout the talk and result. Other possibilities that matter is supplied from companion star, and due to gaining matter, gravitational power increases, that shrinks the size, that again from flux freezing increases magnetic field, and new trajectory emerges from the Chandrasekhar trajectory. And that can be easily seen by following simple conservation law, neglecting, of course, detailed CV physics, toy model, linear momentum, angular momentum, and flux conservation, if you consider, you can show by 10 to the power 9 to 10 years, surface field could be 10 to the power 11 Gauss, and central field could be 3 order of magnitude higher. So strong field white dwarf is not a very puzzle. It is there, theoretically. We simulated a few years back XNS code-based result. We found that rotating toroidally dominated white dwarfs could have different shape depending on the geometry. If rotation is low, then it is almost spherical, but inner region is prolate shape. But if rotation is high, then it is overall oblate shape. For differential rotation, it is kind of having polar holo-like structure, and some of them could have mass 2.5 solar mass or so, obeying magnetic to gravitational energy ratio in this range. So they would be okay with stable equilibrium condition, at least some of them, with high mass. With this basic recapitulation, what we have been working over the last several years, and this part I have presented so far have been presented in other meetings as well. Now the very new thing what I am presenting in the present meeting is non-rotating magnetized white dwarf in finite temperature. So we have set of model equations. This is pressure balance, hydrostatic balance equation. We have self-consistently considered all three components of the pressure: degenerate pressure, ideal gas pressure, and magnetic pressure. The radius at which ideal gas pressure dominates degenerate pressure, that is the initiation of envelope to the surface. That way, envelope core interface is defined by default, not by hand, comes automatically by solution. Then temperature gradient determined by the two terms. This is radiative term, this is convective term. If convection is dominated, this is determined, this temperature gradient. But most of the calculation of what we have done based on magnetic field, this is subdominant. So it is radiative white dwarf in the core region at least. So this is dominating. With this finite temperature effect, if I plot mass radius relation, low mass region, you see Chandra's black curve is deviated. Basically, result is deviated from Chandra's black curve. For a given radius, you see mass increases, maybe slight, but still thermal energy due to dTdr equation holds extra energy and extra mass. So, but that does not affect high mass region. High mass region exclusively is arising due to high magnetic field. If field is 10 to the power 14 Gauss at the center and surface is reasonably low, you see mass could be, mass radius relation deviates significantly from Chandra's mass radius relation, and it could be all the 1.9 solar mass, even for non-rotating case. And that is purely magnetic field effect, but temperature gradient does not have much effect here. So this is overall magnetic field and temperature based idea. Again, theory and simulation results match perfectly. Now, when you have high magnetic field, to have stable equilibrium, magnetic field has to be introduced at the expense of thermal, magnetic effect has to be included at the expense of thermal effect. So for stable equilibrium, you have to have lower thermal pressure. So right hand side is almost similar. Mass radius do not change significantly, but if strong magnetic pressure is introduced, it has to be at the expense of thermal pressure at a given gravitational energy. That is why all the highly magnetized super Chandra white dwarfs are lowly luminous. That could be again established by solving the set of equations. This region, this all region, this magenta and blue curves are basically highly magnetized finite temperature super Chandra white dwarfs. But luminosity, if I go to the next slide, say to 2000 kilometer white dwarf, this is the field, this is the luminosity, 10 to the minus 16 solar luminosity, and mass 1.9 solar mass. Without magnetic field, and its mass is 1.38 solar mass only, and density is about 2 × 10 to the power 9 gram per cc at the center. So no problem with even pictonuclear reactions. So super Chandra, but very dim. That's one of the reasons, very difficult to detect them. They're in the lower left corner of the Argon diagram. Sorry, the HR diagram. Sorry, I'm talking to my student who is presenting fluid part and accretion disk session discussing Argon diagram. What about cooling and ohmic and Hall decay? These also play a very important role. Field has to decay over the time. It cannot be that strong. First, cooling. By simple cooling law, we see if it cools down, thermal energy again goes off. Again, you know, this green curve, green and blue curve, which are overlapped completely with other curves, but you see it comes slowly towards red black curve, which is Chandrasekhar's master distillation. So whatever extra effect came due to thermal effect due to cooling, again it approaches to Chandrasekhar's master distillation. So cooling again for a given radius decreases mass, low density and low mass region, but high mass region cooling doesn't have significant effect, but effect is due to magnetic field. Ohmic and Hall, these are the two important decay effect takes place for the field 10 to the power 14 Gauss or less. Till 10 to the power 13 or 12 Gauss, it is Hall. Below that is Ohmic dissipation. That decays field. And it is a field which holds extra mass. If field decays, mass again goes off, sets off, then this Super Chandra mass radius curve now merges, at least not merging, but at least goes off, and it becomes 1.5 solar mass. And that would happen if age is beyond 10 to the power 5 to 6 years. After 10 to the power 5 to 6 years, there is no change. Decays will not work. Magnetic field hardly decays. It remains Super Chandra. So if you have to really detect them, you have to detect by 10 to the power 6 years of its birth. So otherwise, it will not remain Super Chandra. It will not remain massive. That's a very important take-home message here. Field decay. So here you see, for 2000 kilometer white dwarf, at the beginning, 1.86 solar mass white dwarf of low luminosity, but at 10 giga-year, field decays by factor of 2, and immediately by factor of 2 low field, the Hall decay plays important role and mass becomes 1.54 only. So it is Super Chandra, but quite slightly Super Chandra. So decay makes magnetic field decays destroy the massive white dwarf. Very last 1.5 minutes. So then how to detect? They are dim, they are not remain Super Chandra more than million years. Then how to detect? Maybe gravitational wave surge would be playing very important role. They are triaxial, and rotation and magnetic axis if are having finite value chi, and they are rotating in any case, both of them are contributing to strain rate. And if they are finite, they can actually triaxial white dwarfs could have significant gravitational wave radiation. But remember, if they have strong dipole radiation, very fast chi and omega changes and goes to 0. So if you have toroidally dominated field, which again have been Cambridge stars code successfully developed, that is the final situation of white dwarf, toroidally dominated. Then actually dipole luminosity is not significant. So the chi will remain finite and omega remain finite for significant time. One such case I consider that toroidally centrally dominated into the 14 Gauss and polaridally surfaced into 10 Gauss. If this white dwarf I consider and look at gravitational radiation, I'm almost done. My time is over. That it tells that LISA 1-year curve actually should be able to detect. This is LISA 1-year curve. This is LISA 1-year curve, and this is the gravitational radiation. Strain 10 to the minus 20 should be detected actually, and it will remain for long period. If it is polaridally dominated, on the other hand, sorry, this is toroidally dominated. This blue one still above LISA 1 year. If it is, sorry, no, this is toroidally dominated, quite above 1 year LISA. But if it is polaridally dominated, it goes down, but still it is above LISA 1 year curve. However, they may not be survive longer, so they have to be detected very fast. Otherwise, they will go off because of strong dipole, and they are also not countering confusion noise. They are above all those shaded region. So gravitational wave could play important role. So I'll summarize. So highly magnetized. So this is last slide. Highly magnetized stable white dwarfs have a variety of implications. Sorry.
That's okay.
So numerical simulations of Cambridge stars argue white dwarfs to be toroidally dominated, and they could give rise to new generic mass limit, which is more than 2 solar mass. They are triaxial and very difficult to observe or rare, because due to decaying field, hence not remain massive longer, and they are also losing pulsar nature first and low luminosity. So they could be, however, very good candidate for LISA 1-year curve. Also, BBO DESIGO futuristic missions could help determining them. So appropriate mission in GW astronomy or otherwise radio astronomy should be planned to probe them. Thanks.
Very much. Thank you very much, Bani, by your talk. So some question? Have someone that wants to make any question?
Yes, I have one question.
Yes, Quantai, please, directly, fast.
Okay, you show that your magnetic field is quite high, 10 to 14 Gauss. But
central region.
But do you observe this kind of magnetic field? Because it is quite huge, I think, for white dwarf.
No, it is simulated by numerical. Just see, by numerical simulation, we are able to get it from main sequence, as I showed you. By main sequence star, when star is collapsing to form a white dwarf, we are able to get central field in the power 14 Gauss. And second, still it is under equipartition, and even with this field, size decreases. Still, we find magnetic to gravitational energy ratio is well below 0.1, 0.05 or so. So even that way, if you think of, say, Braithwaite condition, still satisfied, if that has to be taken seriously, because that is also geometry dependent. So I don't think the 14 Gauss is quite high.
But what about
higher
stability
side,
of the system? Because this donut shape and huge magnetic field, I think a system is not stable.
No, it is stable. Donut shape is for differential rotation. Donut shape is differential rotation. You are talking about this one?
Yes, yes.
This is differential rotation. Left hand side is uniform rotation. It is quite stable. You can do stability analysis, and as I said, even simulation result is quite stable, robust.
But have you checked the virial theorem for this system?
Yes, you can look at my paper. Okay, this paper. Actually, you have to modify virial theorem. This year we published a paper. We have shown that if you have strong magnetic, see virial theorem, for example, Sapir-Tucholsky. The virial theorem, what is defined there, assuming magnetic pressure is negligible. If you consider magnetic pressure playing important role, you have to re-derive virial theorem, and accordingly you have to have modified coefficients of various terms in the virial equilibrium. You look at our paper, which will tell you there is no violation of virial theorem either. You have to be careful about virial theorem. People did mistake earlier, I know. They consider old virial theorem, which is assuming in the first place magnetic pressure is 0. But here magnetic pressure is not 0. You have to recalculate all the coefficients. Look at our paper.
Yes, thank you. Yeah, you are in fact right in this thing that things can change. Of course, you know that surface you only have 10 to 9 Gauss until now. So it's 5 orders of magnitude larger in the center. That, I don't know, it's maybe hard to believe, but it's possible at least. But I don't know, it's not easy, but that's fine. Okay, so let's continue now.
By numerical simulation also we are getting manual. It is not theory, even by numerical simulation we are getting.
No, yes. Numerical simulation, everything is perfect. No doubt. It's
that is why Christopher Tout is helping me.
It will happen. That's the only thing that may be, but okay, no one knows. Yeah. Okay, so let's continue. Next speaker now.
I'll answer, or it is already say.
Now in the list, I think it's yes, Deb. Yes. Thank you very much.
Yes.
Can begin. can begin.
Mic is off.
Devabrata, you can start.
The microphone is off, Deb, please. So begin again.
Am I audible?
Now it's okay. Begin.
Yes.
Okay. Okay. Hello, everyone. Thank you for the opportunity to present my work in this session. The work I'm going to present is study the effect of anisotropy on the highly magnetized warp drop, which is in collaboration with Professor Banibrata Mukhopadhyay. So before I start what we have done in this work, let me revisit some introductory ideas. So the series of observation of several peculiar overluminous type 1a supernova as shown in this plot are best explained by the massive progenitor white dwarfs having mass beyond the standard critical mass limit of 1.4 solar mass introduced by Chandrasekhar. So researchers have predicted that overluminous SN 2009 IF requires the possible progenitor white dwarf of mass as high as 2.8 solar mass. Such massive white dwarfs beyond the critical mass limits are popularly known as super Chandrasekhar progenitor white dwarfs. Immediately to explain this peculiar astrophysical scenario, researcher came up with two possible explanations. One is merger of massive white dwarfs, and other is exploration of rapidly rotating white dwarfs. However, immediately researchers found these competing progenitor scenarios have failed to explain such highly massive super Chandrasekhar progenitor white dwarfs. Interestingly, Mukhopadhyay and collaborator introduced a magnetic white dwarf model which can suitably explain such super Chandrasekhar white dwarfs, assuming high magnetic field within the stellar structure. And for the last 10 years, Mukhopadhyay and group came up with different, many sophisticated model that can actually explain such super and sub Chandrasekhar white dwarfs. Now, to address the issue whether the maximum mass of compact stellar object increase or decrease due to presence of strong magnetic field, Chu et al. In their work introduced the idea of magnetic field orientation. By magnetic field orientation, they mean that when local magnetic field are directed toward the radial direction, this is termed as radial orientation, and when the magnetic fields are oriented in the direction perpendicular to the radial direction, say along theta direction, they are termed as transverse orientation. And Chu et al. In their work find that the strain, beside the strain of the magnetic field, the magnetic field orientation has significant effect on the maximum mass of the stellar object. However, they did not include this magnetic field orientation effect and pressure anisotropy due to the presence of magnetic field in their TOV equation explicitly. As a result, they did not able to predict the effect of magnetic field orientation and the pressure anisotropy on the physical parameters inside the magnetized stars. So this motivates us to include and investigate the in detail the properties of anisotropic white dwarfs by considering the effect of magnetic field orientation and its spatial distribution in the TOV equation, which Chu et al. Actually ignored. Also importantly, in this present study, we have considered another thing. We have considered effective anisotropy, which is coming due to both the local anisotropy of the fluid and presence of strong magnetic field. And we are going to see that this effective anisotropy thing will play a crucial role for the stability of the anisotropic and magnetized white dwarf at their stellar core. So the essential stellar structure equation required to describe static anisotropic spherical symmetric compact object in the presence of strong magnetic field as shown in the equation number 1 and equation number 2. So these are the TOV equation. So from equation number 2, one can easily see that the effect of magnetic field strength, magnetic field orientation, and anisotropy are well taken within the TOV equation, where this delta is the combined anisotropy due to both the matter and field. Here rho is the matter density, PR is the matter radial pressure, and this PT is the matter tangential pressure. Now let us discuss another thing. If one ignore anisotropy due to the matter and only consider anisotropy due to the magnetic field, what will happen? So if one consider isotopic matter distribution, then immediately we have PR equals to PT, that isotopic pressure. As a result, the anisotropy factor will be proportional to B square. You can see that anisotropy factor can be proportional to B square, and which has non-zero value at the stellar center. So anisotropic force also have non-zero value at the stellar center. Now, for any compact stellar object, you can see the hydrostatic force. This one is 0 at the center, and the gravitational force also 0 at the center. But due to the choice of isotropic matter distribution, the in the presence of magnetic field, the anisotropic force is non-zero at the center, which immediately triggers instability at the stellar core due to the non-equilibrium of the forces. And definitely this situation can be taken care, as we have considered, this can be taken care by considering effective anisotropy due to combined effect coming from local matter anisotropy and the magnetic field, which is already present there. So to close the system of equation, we require a functional form for the anisotropy, which should maintain the essential assumptions like anisotropy and anisotropic force should be 0 at the center. It should vary from the center to the surface and depend non-linearly with the radial pressure. Also within the functional form of the anisotropy, the effect of magnetic field and its orientation should be taken care. Also the effective anisotropy idea, that is the effective anisotropy coming from the effect from both the matter and field, should be included there. To this end, we have modified the well-known Boyle-Young anisotropic form as given in the equation number 3, and you can see all those ideas included in this functional form. And here kappa is actually a dimensionless constant which actually controls strength of pressure and anisotropy within the system, and we choose value of kappa will within the permissible range as given as already predicted by Silva et al. So describe the matter distribution for white dwarf. We choose Chandrasekhar equation state as given in equation number 4, where the symbols have usual meaning. For example, m is the mass of the electron, mh is the mass of the hydrogen atom, mu is the mean molecular weight per electron, and we choose mu e equals to 2 to predict the carbon oxygen white dwarf actually. Further, following Bandyopadhyay et al., we have considered the density dependent magnetic field profile as given in the equation number 5. Here Bs is the surface magnetic field, B0 is a constant parameter proportional to the central magnetic field. For this work, we have chosen value of surface magnetic field as 10⁹ Gauss. However, we find that our model is not sensitive with the choice of surface magnetic field. Here you can see another constant parameters like eta and gamma, which actually controls how magnetic field decay from the center to the surface. So for the presentation purpose, we choose a presentation purpose for the achieved results. We choose a 1.3 solar mass magnetized white dwarf candidate, and in the extreme, which have, as I already said, 10⁹ Gauss surface magnetic field. And in the extreme left panel, you can see the variation of the profile for the matter density for the changes of B0. So there is effect of 2 orientation of magnetic field. For the transverse orientation, as the values of B0 increases, you can find the density decreases gradually. However, for the radial orientation, as the values of B0 increases, density profile for the density becomes stiffer. And same phenomena can be seen for all the pressures in the middle panel for the radial pressure and in the extreme right panel for the tangential pressure too. We have also plotted the system pressure, like variation of the system pressure with the system density. What I mean by system pressure, system parallel pressure is the pressure along the magnetic field, and that transverse pressure is the pressure perpendicular to the magnetic field, which has contribution from both the matter and field. So you can see for the radial orientation, as the value of B0 increases, both the pressure becomes stiffened. However, for the transverse orientation, as the value of B0 increases, the pressures become softer. And note that for at the center, all the pressures have same value, that is 0 anisotropy prevails there, which is important for the consistency of TUV equation. And this is more clear if we plot the anisotropy profile here. You can see at the center and surface anisotropy is 0 to be consistent with the TUV equation. Further, we have shown variation of the MR curve for the different value of B0 kappa and magnetic field orientation. Here in the extreme left plot, you can see a cyan color plot. This is the case for the Chandrasekhar mass radius curve when there is no magnetic field and anisotropy also not taken. So you can see for the other cases, as the values of B0 increases for the transverse orientation, we can achieve high mass and high mass maximum white dwarfs. So we set the values of B0 for the transverse orientation in such a way that we can predict two progenitor of the super overluminous supernova at 2.1 and 2.8 solar mass. And likewise, for the radial orientation, if you increase the value of B0, you can see the mass of the star and its corresponding radius decreases gradually. In the middle panel, we try to investigate what will happen if we increase the values of kappa, that is the constant parameter within the star. So as the values of kappa increases, you can see the maximum mass for the white dwarf also increases. And in the extreme right panel, we try to investigate by changing the gradient of the magnetic field. So if we increase the gradient of the magnetic field, that is, if we increase gamma and eta gradually, you can find the maximum mass of the white dwarf increases gradually. In this plot, we also try to explore the combination of the substandard and super Chandrasekhar white dwarf through single MR curves. So let me explain the left panel curve. Here you can see for the different values of B0 and kappa, one can find standard and super and sub and standard Chandrasekhar white dwarf. And in the middle panel, for the fixed value of kappa and varying value of B0, one can find sub Chandrasekhar and super Chandrasekhar white dwarf and standard and super Chandrasekhar white dwarf through single MR curve. And if one fixes B0 value and varies the kappa value, that anisotropy factor, one can easily get sub Chandrasekhar, standard Chandrasekhar, and sub Chandrasekhar, super Chandrasekhar, standard Chandrasekhar, and super Chandrasekhar, all this combination through single MR curve. Then we try to see the variation of maximum mass with the central magnetic field for the increasing value of central magnetic field. You can see, as already I have mentioned, that for the transverse orientation, with the increasing value of central magnetic field, the maximum mass increases. However, for the radial orientation, it is decreasing. Beyond certain threshold central magnetic field, it is nearly 3 into 10 to the 13 Gauss. Also, we have checked M versus central density plot. Here we found up to the maximum mass point, the dm by d rho c greater than 0, this condition prevailed, and this says stability of this present model. And to investigate the hydrostatic equilibrium or stability of the model, we have also plotted we have also investigated variation of the ratio of magnetic energy to gravitational energy ratio with the central magnetic field. You can see both the orientation. If we choose high central magnetic field, say like 2 or 3 into 10 to the 14 Gauss, even for that case also the ratio is around 10 to the minus 2, well below than the critical value 1 as predicted by Chandrasekhar and Fermi. So we can say our model is stable with this high 10 to the 14 Gauss central magnetic field. Further, we also try to see variation of adiabatic index for the all cases, and find that for all the cases, it is way above the value of critical value 4/3, and it actually predicts stability or physical validity of our result. So finally, the highlight of the major results are, through this work, we show that to maintain magnetohydrostatic stability in the stellar core of B white dwarfs or magnetic white dwarfs, it is important to consider combined effects of anisotropy due to both the local anisotropy due to the matter and the magnetic field. Also, by choosing different values for the constant parameters like B0 and kappa, it is possible to predict the highly massive progenitor of peculiar overluminous type 1 supernovae, that is the super Chandrasekhar white dwarfs, which is way beyond the value of critical mass limit 1.4 solar mass, and they're also related to standard idea of standard candle. So these things, so we can actually pass beyond this critical mass limit, and this questions the idea of critical mass limit also. So through our work, we able to explain the possible combination of sub and standard Chandrasekhar progenitor B white dwarfs, standard and super Chandrasekhar B white dwarfs, and sub and super Chandrasekhar progenitor B white dwarfs via single mass radius curve for the respective cases. I am thankful to my co-author, Professor Banibrata Mukhopadhyay. Thank you. That's it.
Thank
So
you
I am
very
now
much.
open to questions.
Thank you very much, Def, for your talk. Some question? You have some question to make?
May I have one question?
Yes.
In your slide 13, I think I saw last plot, and I don't understand the meaning of the plot. 13.
13. Okay.
Yes.
Yes.
So it's like a mass radius relation, but the
Yes.
last
Yes.
and why you have non-stable white dwarfs there? Because usually we consider only stable white dwarfs.
No, so non-stable, we try to show actually combination of the standard and super Chandrasekhar white dwarfs through the single mass radius plot. So here you can see, here is the standard through the same mass radius plot. You can see there is the standard Chandrasekhar white dwarf, and this is the super Chandrasekhar white dwarf. However, this branch is not stable. So it is okay, it is not stable, but all other branches like this branch and this branch are stable. So we can accommodate all the peculiar oval-luminous supernovae through the single MR curve. That is the main idea behind these plots.
As well as underluminous.
It's like you have different types
Yes.
of white dwarfs. So this is very interesting and intriguing. Okay, thank you.
Okay.
Thank you very much. So let's continue for the next speaker. Now is Cláudia Rodrigues from Instituto Nacional de Pesquisas Espaciais from Brazil. So be free to begin.
Okay, thank you. Are you seeing my screen?
Yes, perfectly.
Okay, thank you. Thank you very much for the invitation, for the opportunity of giving this talk. I'm going to change a little bit the flavor of the talk. I'm going to talk about white dwarfs in a more observational perspective. In particularly, I'm going to talk about the discovery of the system as a very fast spinning and magnetic white dwarf. So first of all, I'd like to change my slide. So this is a very simple plot, but I think it's very important to understand the white dwarfs. I think what are the key parameters that you have to have. The parameters that you have to observe, determine in the sample of white dwarfs are the mass, the spin, and the magnetic field. If you understand how these values are distributed and the white dwarfs in the universe, we can understand what are the white dwarfs, what are the evolution paths that result in what you see. And on top of these three parameters, we have also to have in mind that it's important to know if you are talking about isolated white dwarfs or we are talking about binary white dwarfs. And this is important in the present day and also as in an evolutionary context. So I will give you some correlations of observed systems. In isolated white dwarfs, we see that high values of rotation, mass, and magnetic fields seem to appear together. So here I give two examples of very, very the objects that have very high magnetic fields observed, measured. They are very fast. They have spins of around minutes, and at least the second of them is probably near Chandrasekhar white dwarf. In fact, this is a object that was just being discovered. And here we're talking about isolated white dwarfs. If we think about rotation, about angular velocity, we see, oh, no, this is very important. Probably these objects are result of a merger, but more work on that should be done before we have this scenario confirmed. Anyway, if we think about rotation, the fastest white dwarfs are all located in binaries. I'm going to talk about one of them, one that you have discovered as a fast rotator, but I'm going to talk and also about the other objects in this important class of white dwarfs. So I'm going to talk about CTCV. I'm not going to try to say all those numbers. My English is bad, and if I try to say these numbers, it will be worse. But this system, CTCV, it's an example of a white dwarf in a binary system which has a very high spin, and it has a no negligible magnetic field. The magnetic field is important in the object, but it's not huge probably. It's important, but not extreme. So this system is part of a class called intermediate polars. It's a cataclysmic variable, which is a compact binary formed by a white dwarf plus a low mass star, and in which you have mass accretion probably in most or in all systems by this mass accretion is caused by Roche-Loeb overflow. If you think about the intermediate polars specifically, they have a magnetic field that of around a few megagauss, in some a bit higher, in some a bit lower. But what is important is that the magnetic field is not high enough to synchronize the periods of the white dwarf and the secondary star, but it is high enough to have an effect on the dynamic of the mass flux, on the mass flow from the secondary to the white dwarf. So in some intermediate polars, we see a disk, an accretion disk, and some we don't have an accretion disk. But in all of them, we have a magnetic accretion structure. Okay, and when this structure, or in the part of this structure that is near the white dwarf surface, we have a shock. The shock is responsible by a density enhancement. So we have a very bright portion of the system. And as we see the white dwarf rotating, and you see this post-shock region varying, the viewing angle of this region varying in our perspective, in our observer perspective, we see modulation. And this modulation can be observed in X-rays and in optical wavelengths. So going back to CTCV, as a system, as a compact binary, as a cataclysmic variable, this object was discovered 10 years ago. In this paper, the authors show the radial velocity of the emission lines that has a behavior that indicates without any doubt that you are talking about a compact binary. This system is an X-ray source, so this is a hint that you are talking about a magnetic CV, because the X-ray emission comes from the post-shock region. And in this paper, the authors suggest a photometric period of around 15 minutes that, if real, could be related to the rotation of the white dwarf. And in this case, the system would be an intermediate polar. So some years later, Albert Bruch made an extensive photometry of the system, and he could not confirm this periodicity. Okay, and here I show an optical spectrum of the system that we have in a survey, or in a survey in which we have found some new magnetic CVs. And in this optical spectrum, what you see is that we have accretion, but it's not clear that we have an accretion disk. Anyway, so to understand more the system, we asked the XMM Newton data, and this data show very clear signal. It's a Fourier how to say, a Fourier transform that has a peak that's almost unbelievable, almost as the one that you see in pulsars. And this period is reflected in this diagram phase, in this light curve in X-rays, a very clear modulation. And we have visited the optical data from Albert Bruch that was collected some years before, and the signal was there. And was there with exactly the same frequency, with no change from year to year. So we are very confident that you are seeing the white dwarf rotation. So we are seeing a post-shock moving accordingly with the white dwarf rotation. Okay, so if we go a bit deeper in the X-ray emission, the X-ray spectrum is completely consistent with accretion.
Claudia,
Yes.
10 minutes already. Okay.
Okay. Oh, Manuel, I lose the. Okay.
You are talking. I don't know. Oh no, I don't know how many slides you have. So
no, I have a lot of them. The last ones are the more interesting. I would like to have time to discuss them with all of you. And so the emission, the X-ray emission is completely consistent with accretion scenario. What we have already seen in optical wavelengths. So differently from standard intermediate polars, the luminosity of the system is low, is 2 orders of magnitude lower than the unstandard IPE. And if CTCV is not alone in this group of low luminosity intermediate polars. In fact, we have a group of around 10 systems. Probably the low number of systems in this group is because they are very difficult to detect it. Probably with E Rosita, the thing will change. the scenario can change. It can confirm if this group is really an important group of intermediate polar, if it is a group with lots of members, and because if it is the case, if you are talking about the tip of an iceberg of intermediate polars, they can be responsible by the X-ray galactic background. Okay, so can we have a faster spinning white dwarf? Let's see. W zeta Sagittae is a standard cataclysmic variable. Its period is smaller than the period of CTCV, but this period is sometimes present, sometimes is not present. Sometimes you see two periods very similar, but not coincident. It's very difficult to say by sure that you are talking, that you are seeing the white dwarf rotation. Another important object, very famous, is this one. It's a compact object that's rotating a relatively fast, with a relatively fast velocity. And considering the luminosity of the system, it's probably a neutron star, because it is, considering the distance the object have, that now you know the distance thanks to Gaia, considering the Gaia distance, the object has a very low luminosity, or a very low luminosity, and this is not consistent with white dwarf origin. Maybe a more controversial possibility of faster white dwarfs is in the context that some part of the so-called magnetars, the gamma ray repeaters and the anomalous X-ray pulsars, are not neutron stars but white dwarfs. This is an idea that which has been developed in the last decade, and it's quite possible that part of the magnetars can be in fact white dwarfs and not neutron stars. And just or an example of a fitting of the real observed emission of one magnetar, of this one, Sarah Borges and a group of colleagues, including me, we have fit the spectral energy distribution of this object in the context of fast spinning, massive and magnetic white dwarf. And in this case, the spin is around 9 seconds, so it should be faster than CTCV. Okay. An important aspect related to previous talks is that the spin of a white dwarf can put constraints on the material and on the equation of state of a white dwarf. And for CTCV, Otoniel and colleagues they have a preprint in which they show the white dwarf magnetic, the white dwarf mass of CTCV is at least 0.56 solar masses. So now let's move to compare CTCV with other fast spinning white dwarfs, systems that you know that are white dwarfs. They are the fastest white dwarfs that we know. All
17 minutes.
Okay. So now we are talking about AE Aquaria and V4060 Hercules. Both objects are cataclysmic variables in a relatively high, which is in a relatively large system, and they have a secondary that is out of the thermal equilibrium, probably because a previous phase of high accretion that could be the responsible by the fast rotation seen in these objects. But in the case of CTCV, what has caused the high rotation? Maybe CTCV is the future of systems like those, because its cataclysmic variables evolves from high orbital period to small orbital period. The orbital period of CTCV is less than 2 hours. So it is in the region of the more evolved cataclysmic variables. So I let you with my conclusions. I thank you for your attention, and I am happy to answer any questions that we have time. Thank you very much.
Thank you, Claudia, for your very clear talk. And if someone has one question, please be free to make. No questions?
Can I ask one?
Yes.
Please?
In the beginning of one of your slides, you showed that highly magnetized white dwarfs are usually in the binaries. Is there any particular reason for that, physical reason why it would be the case?
Probably because the accretion is playing a role in spinning up the systems, because in isolated white dwarfs, probably the mechanism to spin up the white dwarf is or they are fast spinning because they are the result of a merger. And if the white dwarf is in a binary, the accretion can transfer angular momentum from the stream from the system to the white dwarf. I
I got it. Yeah, thanks. Yeah, sure, thanks.
Yeah. And nowadays, at least seems that the people are trying to identify white dwarfs from mergers with three things, these three axes that Claudia just spoke. Very massive, very magnetic, and very fast. Let's see if these three things are really seen in other isolated ones. Okay, but seems that they are very magnetic, at least is what you have from these two. Okay, and one already very massive. And okay, let's continue now. Thanks, Claudia, okay, for your talk. Okay, thank you very much. And now, sorry, what happens here? What happens here? Something happened with me. Okay, so now the next speaker is Peter Menches from South Africa. Okay, thank you very much for being here. And he's talking about some of these fast white dwarf pulsars.
Just see.
And maybe if you can try full screen, be better.
Can you see this? Can you see the screen?
Yes, but not full screen. Not full screen. Slideshow, yeah.
You should. Let me see.
Maybe there in slideshow.
Maybe just get stop. Yeah, it looks like I cannot find the slideshow option here. I don't know where it is.
In app slideshow, in that part, animation slideshow, I see. Maybe it's not there. Slideshow. No,
Try to
just
push F5. Maybe it works. F5.
Again?
F5. F5.
F5.
Try to see. No? No. Then you should go to slideshow in this panel.
Yeah, slideshow.
Exactly.
It's in the menu up. Yes. In the menu up is slideshow.
In the
You
top
don't see
menu.
slideshow?
No?
Huh?
In the top.
Where you have file, home, insert.
Where? Sylvia?
Right. Let me just see if I can find it
Up.
there.
Where is file? On the right, home, insert, design, transition, animation, and slideshow.
It's in the middle. Go to the upper panel. It's in the middle.
Menu. Yeah. You don't see file, home, design, animation, and slideshow?
Ah, sorry, yeah.
Yes.
Yeah. Sorry.
There. Yeah.
That the panel blocked it, so I couldn't see it.
I
Sorry for that.
Yeah, F5.
Okay. Sorry, thank you very much.
Okay.
Sorry for this delay.
Perfect.
Yeah.
Perfect.
Thank you for this invitation. So in this presentation, I'm going to talk a little bit about particle acceleration and high energy emission in two closed binary systems, AE Query and AR Scorpio. And in the process, I'm also going to present some of the results of my MSc students that finished their PhD, the MSc thesis recently. So the layout of the presentation, I'm going to say a few words about particle acceleration in white dwarf magnetospheres, but I'm going to touch it on it very briefly. And then I'm going to introduce the two sources that I'm going to talk about, AE Query and AR Scorpio. I'm going to say a little bit about their multi-frequency properties. And then I'm going to present some data that we obtained recently with Meerkat and also Fermi Lat of these two sources. And maybe if there's time, some conclusions. So if we look at rotating magnets, we know that a magnet that can rotate with a certain velocity v relative to a static medium can induce an electric field. This is the equation for the electric field, the induced field in the frame of the laboratory reference frame. If we transform the laboratory magnetic field to the magnetic field in the frame of the source, the equation looks like this. Now we know that if that electric field can be sustained for a certain distance, delta S, then any charge can acquire a certain energy, which is given by this equation here. And obviously this can then be cast in the following form, where the maximum energy is now represented by the rotational speed of the fast rotating white dwarf. Here is the gamma factor associated with that. This is the size of the source, and this is the magnetic field in the frame of the source. So in this Hillas diagram, these authors showed that white dwarfs can, in principle, accelerate charged particles to energies up to the order of 10 to the 20 electron volt. But obviously, this is highly idealistic. We know that particle acceleration in magnetospheres is a very difficult topic, and it is not so easy to accelerate particles in conducting plasmas. So what you need from that equation that I showed on the previous slide is obviously a fast rotating white dwarf with a strong magnetic field. And AE Query, the white dwarf in AE Query is definitely a good contender for that, with a rotation speed of 33 seconds. We also, we also know from the optical observations that the white dwarf contains shows rapid variations in optical wavelengths with magnitudes ranging up to 2 over timescales from minutes to hours. The power spectrum that you see there shows the pulse period of the white dwarf, the 33 seconds, and also the associated first harmonic at 16.5 seconds. And during flares, there are some QPO activity also that you can see in that bottom panel. What was quite curious from this first studies of this source was the low pulsed fraction, less than 1%, which was suspiciously low for a disk accreting white dwarf. We must remember that at that stage, it was believed that AE Quaerae is a disk accreting system. But we know that from recent studies that the system is in a very high propeller state at the moment, because the rotation velocity of the magnetosphere is much higher than the Kepler orbital velocity of the material that is transferred from the secondary star. And as a result of this mismatch in the rotation speed, the material is in fact ejected from the system in terms of this very effective propeller mechanism. As a result of this magnetic interaction between the magnetosphere of the white dwarf and the plasma, the white dwarf in AE Quaerae is losing orbital velocity because it's transferring some of its rotational kinetic energy to the plasma, ejecting it out of the system. So the spin down luminosity of the system is of the order of 10 to the 34 ergs per second. The other system that I want to touch on is AR Scorpii, that was in the headlines quite recently since the discovery paper in Nature in 2016 by these authors. What is remarkable about this system is that it shows high amplitude oscillations over a wide frequency range from optical up to radio frequencies. So this is nothing else than basically a beat period between the rotation period of the white dwarf and the orbital period of the system. And frequency spectra also show that you can definitely disentangle both the rotation period and the beat period. And these authors also show that the white dwarf is spinning down. The spin down timescale of the order of 10 to the 7 years. Another feature of this system is that it is not transferring any mass from the secondary to the white dwarf, and there's also no accretion of material. If you look at the Doppler, or if at the Balmer emission lines from the system, this was by observations that one of my students did a couple of years ago. The Balmer lines clearly follow the orbit of the secondary, and one can actually show that the Balmer lines are associated with the face of the secondary star closest to the white dwarf. And it's believed that a beam of particles from the polar caps of the white dwarf is exciting the material, the plasma, there close to the L1 point, and that is the source of the emission lines. But it looks like the secondary is slightly underfilling its Roche lobe, so there's no mass crossing the L1 region. Another feature of the source is that it shows strong linear polarization in the optical data. The linear polarization is believed to be possibly associated with synchrotron radiation in the system, because synchrotron radiation usually shows high levels of circular polarization. So the data that you see here is consistent with the optical part of the spectrum that is published by Marsh et al. So this is the multi-wavelength spectral energy distributions of both these sources, of AR Scorpii as well as AE Quaerae. And it's obvious that both these systems show emission over a very wide range of frequencies, from radio up to possibly high energy gamma rays in terms of the reports made in the late 80s and early 90s by 2 independent groups. And the remarkable thing about these SEDs is that the emission that you see here is not produced by the accretion of matter. It is most probably be associated with the spin down luminosity of the white dwarf, because that is essentially providing the reservoir that drives most of the emission in both these systems. So let's look at the two sources. AE Query was observed by Meerkat in 2019. Unfortunately, the data set is rather short, about 1 hour. It was observed in the L band. You can see the variability here. This is the lower panel is the total L band, and the other 3 panels are the free channels associated with the L band. And as a result of the source being observed by the full array of 61 dishes, allowing several baselines from 20 meters up to 8 kilometers, we achieved stunning resolution, and one can see that the AE Query was actually resolved as a point source by Meerkat, and I think that is absolutely unbelievable, the resolution that we obtained with this remarkable instrument. The power spectrum, the Lomskakel power spectrum, the Fourier spectrum of AE Query, when we use 8-second and 10-second binning, clearly show pulsed emission associated with the rotation period of the white dwarf. I must emphasize that this is the first detection of pulsed emission of the white dwarf in radio wavelengths, and I'm not aware of any other reports made of pulsed emission associated with the white dwarf rotation in radio. This is the corresponding power spectrum in the lower part of the L band, where the signal to noise was best. And this is the last power spectra that you see here is basically where we determined power spectra of each of the channels individually and stacked all of them to achieve better signal to noise. And you can clearly see the pulsed emission here associated with the rotation period of the white dwarf. As I've mentioned, the first time that it is seen in radio. The spectrum that we determined from the Meerkat measurements shows this power law. And if you take an average spectrum, the average value of the L band, you can see it is consistent with the overall radio spectrum or the overall spectrum of spectral SED of AE Query from radio up to infrared wavelengths, which is associated with the synchrotron emission of relativistic clouds of electrons that are ejected by the magnetosphere of the white dwarf. We modeled this emission in this paper by Meintjes and Venter in 2003. If you are interested in the physics around surrounding this radio emission. Anisotropy was also observed on 3 occasions with Meerkat in the L band. The power spectra, the Fourier spectra associated with the 3 observations, you can see that there's clear indication of pulsed emission at either the beat period or the rotation period, because that is very close together on this scale. This is a stacked power spectrum of all the observations. You can clearly see pulsed emission at either the spin and the beat period. Other studies by Marcotte et al. Show that the radio emission is strongly pulsed at the beat period, which is obviously consistent with the notion that there's a very strong interaction between the fast rotating magnetosphere of the white dwarf and the magnetosphere of the secondary star. So this is the spectrum of Anisotropy, and if we take the average L-band spectrum, one can also see it is consistent with the spectrum that is published by Marsh et al. And also later by Takata et al. When we did an analysis of the Fermi-Lat data, the whole 10-year data set of the PAS-8 data, which is a little bit more advanced than the previous data sets, by doing a standard analysis, one couldn't really see a clear indication of a gamma ray excess in the region of AE Query. But if we produce a bent light curve, where we bent the data in 2-week sections over the whole 10-year cycle, and we zoomed into regions where there's higher than normal activity and do a likelihood analysis of those data sections, one could clearly see that on the sky map, there is now indications of a point source on the location of AE-Query. So if we look at those 2-week data sections where we got higher than normal activity and binned those 2-week sections in 10-minute intervals and produce a Fourier spectrum of each of these 10-minute intervals and stacking them all together, 2-week section by 2-week section, we could clearly see that the stacked power spectra show clear emission at both the spin period of the white dwarf and obviously the second pole, the 16.5 second pulsed emission. And this is consistent with emission that we reported during burst-like events by 2 independent groups. I was involved with one of them, of the 16.5 second pulsed emission during burst events. These 2 pulsed phase light curves are obviously not simultaneous, but they were made contemporaneous by the 2 groups, the one by the Durham group in England and the Potchefstroom group in South Africa. I can just say here that this picture here shows that the power is obviously centered on the source itself, because if you plot the distribution of pulsed power as a function of the number distribution of the pulse power versus the Rayleigh statistic, then one can see that on source you have a clear concentration of high data points here, which obviously are associated with the spin period and the second harmonic. And as you go consistently further away from the source, up to 15 degrees, you get a pure white noise distribution. So this shows that the pulsed gamma ray emission is located on the position of AE-Query. Some of the regions coincided with optical observations made by one of my other students, which clearly show flaring events. And if we analyze those data sections that coincided with the flaring events and also stack all of them together, you could get a periodogram that shows clear pulsed emission at the spin period of the white dwarf. So that is also consistent with previous reports published in the late 80s and 90s by myself and some other people also. So the gamma ray spectra of AE-Query clearly shows a power law. This is basically the time of the blue line here corresponds to data sections where we got clear emission and not upper limits. So you can say that that is sort of a region where the data representing active regions of the data set, where the source shows certain gamma ray activity. And if we made another selection, taking the data set, the parts of the data with significance above 2 sigma, you can see a clear spectral hardening of the spectrum. So that is probably indicative of periods when the source was in a flaring state. Our analysis of AR Scorpio was not so significant. We couldn't get clear indications of emission from the system, and the spectrum that we could produce is consistent with the 2 sigma upper limit threshold of Fermi-Lat over this entire energy range. But when we did a periodic analysis of the total 10-year data set centered on the source, the periodogram actually show pulsed emission at the spin period of the white dwarf, albeit not at a very high significance level. To make absolutely sure that the data is associated with AR Scorpio, we analyzed regions 3 degrees, 5 degrees, and 8 degrees away to see if there's other pulsations that also appear in this region here that could also be associated with noise with exactly the same frequency. And you can see that there's no other indications of pulsed emission. So it may be a low-level emission from AR Scorpio that we see in the Fermi data, but this analysis is still in a very premature phase, and follow-up studies are definitely required to verify this. So if we look at the conclusions, both AE-Query and AR Scorpio was detected with Meerkat and revealed pulsed emission associated with the rotation of the white dwarf. Standard Fermi-Lat analysis of both sources did not reveal any significant emission. However, focusing on data sections with enhanced photon statistics show pulsed emission from A Equarii at the spin period of the white dwarf and at a beat period of in AR Scorpii, albeit at a much lower significance level. So both these systems contain a particle accelerator of some sort, and it may be interesting for follow-up studies with much more advanced Cherenkov telescopes like the CT8 telescope array that hopefully will be operational in the next couple of years. Thank you very much.
Thank you, Peter, for your very interesting talk regarding these white dwarf pulsars. So it's really nice to see them here with so many data. Some question that someone want to make?
I'd like to make a question. It's Claudia.
Yes.
Could you comment on what could cause some cataclysmic variables be seen in radio and in high energy and others not? What is the property that makes it? Is the secondary, or is the property of the secondary?
Yeah, if we look at A Equarii, for example, A Equarii shows a pulse, shows a propeller mechanism. So we believe that the particle acceleration is associated with the magnetospheric propellering, because the magnetosphere of the white dwarf is under severe stress as a result of excavating all this plasma out of the system. So we get a distorted magnetic field lines. You can get magnetic reconnection in these distorted magnetic field lines. In the paper that we've published also on AR Scorpii, the Buckley et al. Paper of 2017, I outlined in great detail the mechanism also applicable for radio emission in AR Scorpii. As a result of this white dwarf magnetosphere pumping the magnetosphere of the secondary, and you are right, when you say that the secondary stars need to be magnetic as well. AR Scorpii, we know that the secondary star is magnetic. Observations and publications by Garnevich et al. Confirm that. So if you have a secondary which is highly magnetic and it is distorted continuously by the strong magnetic field of the white dwarf, you get strong field-aligned potentials that are developed in that magnetosphere that can accelerate particles to very high energies. I can perhaps just show here, we have modeled the emission in AR Scorpii. It was done by a postdoc of mine, where we looked at the white dwarf and also the secondary star, and this part of the spectrum that you see here, and also here by Takata, is clearly associated with synchrotron emission in the magnetosphere of the secondary star as a result of that being pumped continuously by the white dwarf. So you have to have a fast rotating white dwarf, strong magnetic field, and obviously also a secondary star that is magnetic, because then you get a very significant interaction between the two magnetospheres that can accelerate particles and produce high energy emission.
Okay, thank you very much.
Thank you.
Just a quick follow-up. Is there any correlation, because there are some, not many, but some cataclysmic variables that are detected in radio. Is there any correlation of the secondary spectral type with the presence of radio? Is there any study in this direction?
I must just emphasize that the radio emission in both A Equarii and AR Scorpii are definitely non-thermal,
Yes.
emission, in other words, synchrotron. And then there are also other systems, for example, the dwarf novae that shows outflows from the accretion disk. It was shown by one of the people from SAO a number of years ago. I can't remember her name. She's now in America. She showed actually that you can get these outflows from the accretion disk that produce synchrotron emission. So obviously that is a totally different mechanism, and that is also something that I'm very interested in, and I'm starting to investigate this with a student of mine at the moment.
Okay, thank you very much.
I have only one question. The magnetic field of IR Aquarius and the IR Scorpius, they are well defined in some sense. So
They
do
are
you
well
know
defined.
what is the order of this magnetic?
The magnetic field of A Aquarii is about 10 to the 6 Gauss. That is confirmed by circular polarization measurements. The magnetic field of the white dwarf in AR Scorpii is not so well defined. In the paper that we published, we made an upper limit of 250 megagauss, but that is an upper limit. Other studies by, I think, the Carta here shows a magnetic field lower, maybe up to also a few times 10 to the 6 Gauss. So definitely strong magnetic fields, yeah.
Okay, thank you. And you, if I understood you, Aquarius has some burst activity at some time. It has some burst.
Yeah. Yeah, so that was published by us when I was a student many years ago. That was the topic of my MSc and PhD thesis. And it was published in those papers that I have mentioned.
Okay, thank you very much.
One quick comment. Can I make one? Maybe half a minute.
Get to the next speaker is Nicolas Chanel, okay, from France. So Nicolas, if you, okay, thank you very much.
Can you see the screen?
Yes, you can begin when you want.
Okay, so thank you very much for the invitation to this interesting conference and session. So I would like to go back to the microphysics and about weak processes in magnetic white dwarfs, and in the second part also about magnetars. Oops. Can you see the second slide? Can you see the second slide?
No.
Oh.
Didn't come.
Okay, I don't know why. It's, often I have this same problem.
It's PDF, no? So maybe full screen. I don't know. Yeah. Okay.
Can you see the second slide?
Yes, now okay. Perfect.
Okay. And the third slide?
Also okay. Also.
Okay. So I would like to start by recalling some history. So regarding white dwarfs, so the core of a white dwarf, the pressure is so high that atoms are actually crushed, and they consist of ions and free electrons. And quite remarkably, it's Euler who first realized in 1926 that it is the electron degeneracy pressure that allow the white dwarfs to be stable. And several authors, so Anderson first, and then Stoner, Landau, and Chandrasekhar, of course, showed that special relativity leads to a limit on the mass of a white dwarf. But something which has been usually overlooked is that this limit is reached asymptotically when the density goes to infinity. And of course, the simple model of an ideal electron Fermi gas breaks down as the density becomes sufficiently high. So maybe this is also one of the reasons why Eddington was very skeptical about these calculations. Could be, I don't know. But this is an important point, I think. And this can be best seen, I think, on this figure, which is taken from a paper from Stoner, so before Chandrasekhar, actually. But he made the assumptions of a uniform density star. And so you can see here the comparison between so this is the mass as a function of density, electron density. And you can see the calculations without relativity, this is a straight line, and the one with relativity. And you can see that the limit is reached asymptotically as the density becomes higher and higher. And in this case, it was about 1.1 solar mass because of the choice of the mean molecular weight. Now, in the 30s, of course, the neutron was discovered in 1932, and very soon it was realized that sufficiently high density, the properties of matter changes and becomes more and more neutron-rich. And in December 1933, there was this famous announcement by Bad and Zwicky that about the existence of stars made of neutrons, and such stars formed during core collapse supernova explosions. Now, apparently, Bad and Zwicky were unaware of the white dwarf study. They don't mention white dwarfs in their papers. And it seemed that it is Landau, Gamow, and independently Chandrasekhar who made the connection between these two compact objects in the at the end of the 1930s. And here is the quote taken from Chandrasekhar for a presentation he gave in Paris in 1939. Now, it is only at the end of the 50s that actually Avery Schatzman showed that the maximum mass of a white dwarf is actually reached at a finite density. And the reason lies in electron captures. So the captures of electrons by nuclei in the core of neutron stars leads to some instability. And this is the reason why the maximum mass is reached. So I think this paper is quite important. He wrote a book, which is maybe now hard to find. But I think this contribution is quite important. And so why electron captures? After all, a neutron, we know that a neutron in vacuum is stable, and the reason is isn't stable. Is the neutron mass is higher than the proton mass, and therefore a proton has the lower energy, so it's more stable. However, in a dense environment where there are electrons around, then neutrons can become stable because there are no states to decay, essentially. And it is quite simple to estimate the density that we need to reach such state, and it's typically of the order of 10 to the 7 gram per cubic centimeter, at least, depending on, of course, on the composition. And of course, the importance of electron captures for supernova is well known. For type 1a supernova is well known. When white dwarf accretes matter and approaches the Chandrasekhar limit, then essentially the stars explodes, is disrupted due to carbon fusion. Now, as was already discussed at the beginning of this session, a few supernova appears to be overluminous, implying a white dwarf mass well exceeding the Chandrasekhar limit. And different scenarios have been proposed to explain these supernova. And one of these proposals, which I think is interesting, is the possibility that the progenitors consist of strongly magnetized white dwarfs. That was already discussed. In fact, such strongly magnetized white dwarfs were studied a long time ago by Schulman in a series of papers. But at the time, there were not much interest in such exotic object, and these papers were quite forgotten. But he even estimated the mass of such white dwarfs using, well, a lot of approximations and very rough arguments. And he found that the mass could even reach hundreds of solar masses. But of course, it was a very schematic calculations, but the idea was there. Now, again, for such white dwarfs, we should not forget about the electron captures. We pointed out some years ago that these processes can also limit the stability of these stars. So what is the effect of the magnetic field on electrons? Well, the electron motion is quantized into Rabi levels. In fact, it is Isaac Rabi who first found this formula in the full relativistic case. And Landau's paper appeared in the same journal, but a bit later. So maybe you should call it Landau Rabi levels. Anyway, so the main effect of the magnetic field is to make the matter much less compressible, but also to lead to a quantization of electron states. And this quantization leads to typical quantum oscillations on the threshold density for the onset of electron captures as shown on this picture for different compositions. And in fact, we found analytical formulas in the case where there is just one lambda Rabi level occupied, and when we are in this linear regime. And including these calculations include the contribution of electron-ion interactions. Now, what about the consequence on the structure of a white dwarf? So we used the Lorentz code, which is publicly available, to solve consistently both Einstein's equations or Newtonian's equations, in fact, because GR effects are rather small, together with Maxwell's equation. So the magnetic field is not parameterized, but it was obtained from Maxwell's equations. But we assume in this case that the magnetic field is purely poloidal, which is, of course, an idealization. And we know that purely poloidal configuration are unstable, but this was the assumption. And we used also equations of state, including the effect of the magnetic field, but also electron-ion interactions. And of course, there were many other studies studying the structure of magnetic white dwarfs. So here's an example for carbon white dwarfs with a magnetic field at the center of about 10 to the 14 Gauss. And as the magnetic field is increased, the star becomes more and more deformed. So here the magnetic field is, so the magnetic axis is along the z-axis. So if the magnetic field is high enough, then actually the white dwarf gets, well, resembles a donut. So it's at this point, the code breaks down and we can no longer go to higher configurations because there is essentially a void in the middle of the star, which is really exotic. So how about the mass radius curves? So here are examples for oxygen white dwarfs, but it is similar results for carbon white dwarfs. Just showing the effects of electron-ion interactions. So each curve corresponds to fixed magnetic dipole moment because this is actually the quantity which is conserved, which is a constant of motion. And this implies magnetic fields that are not uniform in the star. So the magnetic field is stronger at the center and weaker at the surface. And we can see actually the most important effects of these electron-ion interactions are found for weakly magnetized neutron stars. So this is the red curve or the green curve. And in particular, if you look for 1.4 solar mass neutron star, the radius can change quite a lot, more than a factor of 2 if these interactions are included or not. But with increasing magnetic field strength or magnetic dipole moment, these effects become less and less important. So for strongly magnetized white dwarfs, in fact, it is one can neglect these interactions. It is not a very big approximation. So now, how about electron captures? So here's a figure showing what would be the mass and the radius for the onset of electron captures. So here's an example on this purple curve for fixed magnetic moment. So the circle shows the onset of electron captures for carbon white dwarfs, which thus sets a limit also for the mass. So for oxygen, the mass is even lower. And if we consider that these nuclei, which are quite light, could fuse because of the gravitational pressure, recalling that the densities that can be reached there is of the order of 10 to the 10 or 10 to the 11 gram per cubic centimeters. So such processes may occur. Then if this pycnonuclear fusion occurs, then the mass could be even more reduced. For this configuration, then without nuclear reaction, we can have maximum mass above 2 solar masses. But when these processes are included, then essentially, if it is oxygen, then we have a mass which is even below the Chandrasekhar limit. So this could play a very important role. Here is just to show that this also limits the magnetic field at the center of the star. So this again branches corresponding to fixed magnetic dipole moment, and a given maximum mass translates into a given maximum magnetic field strength. So the two are related. So the weak processes can limit not only the mass but also the magnetic field. Now, in the last minutes, I would like to address also the effects of electron captures, but in magnetars. Soft gamma repeaters and anomalous X-ray pulsars, they are observed to have very high surface magnetic fields, up to a few times 10 to the 15 Gauss, and it is believed that the magnetic field inside could be even stronger.
Nicholas, the slide didn't change. Okay, now change.
Okay, sorry.
The
persistent thermal luminosity of these stars and outburst suggests that there exists some internal heat sources in the crust of these stars, if we assume that they are magnetars. And they are usually attributed to crust quakes. But there are some limitation with crust quake, because obviously the crust must be solid everywhere. And the problem is that these sources must be rather shallow. And in the shallow region, it's not obvious that the crust is actually solid. Now, there is another possibility, which was suggested in 2010 by Cooper and Kaplan, that actually the compression of matter that is induced by the decay of the magnetic field can trigger weak processes, electron captures in the crust. Now, we have to remember that the magnetic field decays on very long time scales. Roughly speaking, is ohmic time, which is about a million years, let's say. So it's a very slow process. So the compression is very slow. So the electron captures actually proceed in two steps. There is a first electron capture in quasi-equilibrium with no heat release. And it is followed by a second electron capture of equilibrium, because the nucleus is usually highly unstable. It's odd, with odd number of nucleons, so it's highly unstable. So it decays very quickly. And this second reaction can release some heat. And at a high enough density or high enough compression, then there can be also some neutron emission. But I will focus here on just purely electron captures. So to compute these processes, of course, we need to know the composition, the initial composition of the crust. So the usual way of calculating the composition is to minimize the Gibbs free energy per nucleon for different pressure. And this has to be performed over essentially all possible nuclei. So it's about 10,000 nuclei. So this can be numerically quite costly, because we don't know what is the initial magnetic field also. So we have to make the calculations for different magnetic field and on a grid, on a pressure grid that is sufficiently small to not miss any layers. But in fact, there is a much faster approach, which I proposed last year, which is iterative, and it's based on some analytical formula. It's very accurate, and it's about 10,000 times faster. And there's a computer code that can be downloaded just to play with that. So here is an example of the initial composition. And this shows the transition density between the different layers in the crust. So when we go to higher density, we go deeper in the crust. And the table on the left just shows the magnetic field strengths in units of 4.4 10 to the 13 Gauss, at which the composition changes, so the equilibrium nuclei changes. So it's just a typical example. Now, once we have the composition, then we can calculate the heat. And this is what we did here. So this figure shows the location of the sources, and the size of the symbol corresponds to the amount of heat. So the bigger the symbol, the more heat is released. So we can see that most of the heat is released at densities between 10 to the 10 and 10 to the 11 gram per cubic centimeter. So in a rather restricted range. And this is for a magnetic field about 10 to the 16 Gauss, which is the kind of magnetic field which is thought to exist in the crustal layers of magnetars. And the amount of heat that is released is of the order of a few hundred keV per nucleon at most. Now, how does it compare to observations? So we can
19 minutes.
Yes, I'm almost done. So we can estimate the time scale for these processes, and it is actually comparable to the kinematic age of HDR and XPs. The amount of heat is essentially independent of the crustal structure. So it doesn't depend on the assumption that the crust is actually solid, so it's quite robust. And the total heat power turns out to be actually the amount that is expected if one is just fitting empirically using cooling models observations. So all these predictions seems to be compatible with observational data. So I think this scenario, which has been overlooked so far, should be further investigated, and of course, fully consistent magnetocooling simulation should be performed to really test this scenario. Okay, here's my conclusions. So regarding the first part, so the maximum mass can indeed be potentially increased by strong magnetic fields. However, the maximum mass as well as the magnetic field depend on the weak processes and especially fusion, which remain highly uncertain. But if super Chandrasekhar exists and are due to the strong magnetic fields, they are probably more likely to behave enough carbon than oxygen, because for carbon, then the onset of these processes is at much higher densities. Now for the second part, for the magnetars, we have a very fast computer code for calculating the composition. We have also very accurate analytical formula for the threshold density, which are actually more accurate than the one that were derived in 2015. And you can find more details in this paper. So thank you, and sorry for the time.
Thank you very much for your very interesting talk. We don't have too much time for questions. I have only one thing to ask you. This analysis for magnetars, they can work for white dwarfs, only that the elements are, of course, not so heavy.
Yes, absolutely. Yes, the formula is just it's analytical, so it's just a function of Z, A. So you can use, of course,
so you can try to see if some bursts mechanisms from these effects can occur in very magnetic and massive white dwarfs also.
Yes. Actually, it's in the magnetic field decays as
well. Because as you know, I don't know, I have this thing that even now they found a very fast one with the size of the moon, very massive, isolated. So I don't know, you see, maybe some burst activities that we see.
But I'm not sure that the whole white dwarf will remain stable, you see, because if the instability hits in at some point, maybe the whole star something will go on with the whole star. So in magnetars, it only occurs in the crust. So it's only a small region. So the star still remains stable. There is it's only magnetic activity, but for white dwarfs, I'm not sure. But you need the magnetic field.
Okay. It's interesting to investigate, because as you know, what I think that why I have always think that some magnetars maybe are white dwarfs, because in that case they are very, very fast. So they are very, very unstable mechanically. The kinetic energy is very close to the gravitational one. And for neutron stars, they are slow. No, but okay, good. So thanks, Nicholas, for your talk. Okay, thank you very much. Let's continue now with Sarah Villanova Borges from University of Wisconsin, Milwaukee, please.
Just a moment. Are you seeing my screen?
Yes.
Okay.
Full screen.
Yeah, I'm gonna put it here. Okay, everyone is seeing full
Yes.
screen?
Yes, speak slow because of the sound, okay?
Okay. So I really wanted to thank you everyone for watching my presentation, and I really hope you like what I'm gonna present. It's like it's still a work in progress, so maybe I'll not be able to answer all your questions, but I hope you like the idea. So I'm gonna talk about the infrared emission of SGR AXPs. As you probably know them as magnetars, but here I'm gonna talk about the infrared emission of them. So I think it's really important to get a few observational things about the class, not the physics itself. So it's a class of very few objects. We have less than 40 objects, and they have a very famous X-ray emissions. So its X-rays has a black body temperature that is roughly 0.4 keV, and a luminosity that can go up to the 10 to the 45 ergs per second. They also have very famous outburst events in high energies, and apart from the soft X-rays, they can emit in radio, infrared, optical, and hard X-rays. So when you talk about X-rays, it was the emission range that inspired the Magnetar model. So we have the Magnetar model to explain the outburst and flare events, and also to explain the efficiency higher than 1 in quiescence. So when you talk about this efficiency higher than 1, what we are saying is that the spin down luminosity is smaller than the X-ray luminosity that we are seeing. So we cannot explain the quiescence X-ray luminosity just by the rotational energy loss. And that's when the idea of the decaying magnetic field comes into the picture. This was in the end corroborated when we started to get the spin down from observation. And we found that the dipole magnetic field inferred by the formula that I am showing this presentation is higher than the quantum limit. Of course, there's a lot of issues with the Magnetar model. That's why alternative models are used. And for example, we have low B sources, high B pulsars. So in this case, we have pulsars that has a dipole magnetic field higher than the quantum limit, but they are not magnetars. And the low B sources are the opposite, magnetars that has a dipole magnetic field smaller than the quantum limit. We also have what we'll be calling antimagnetars. It's not a class, but it's a term that we can see in a few articles that also have the efficiency problem, but a dipole magnetic field that is actually pretty small. And I have talked about the X-rays, and I think that I'm not gonna say much about radio, but I think it's interesting to talk that nowadays radio is also casting a lot of attention because of the RFB-like event that was observed in SGR 1945. So it's a very interesting class for several reasons. And if they have such interest in X-rays and radio, why have decided to focus on infrared? To explain this, I'm gonna do a quick detour from what I intend to say in this presentation. And I'm gonna just show this is the article that me and a few people that are in this part of the meeting today have submitted to the Astrophysical Journal last year. What we basically have done was to show that specifically AXP4U 042+61, which I like to call for U, can be explained by a magnetic white dwarf accreting matter from a disk. I'm not gonna give much detail about this presentation, about this specific work, but if you are interested, I have done a journal author series for the Astrophysical Journal that is on YouTube. So basically the model, as I said, presents an accreting white dwarf surrounded by a disk. And one of the biggest motivations for this work was, in fact, the infrared emission that highly indicates the presence of a disk. And why is that? Because the spectral energy distribution points to a thermal emission. Thermal emission in infrared, the chances that we are seeing a disk, especially in isolated objects, are quite high. And we talk about neutron stars, seeing the disks is quite rare. In fact, we don't see disks, at least confirm the disks in any other neutron star apart from for you. So that's a question, why the disks there? And when we talk about white dwarfs, the pictures is different. We have confirmed disks in about 52%, and 27% of white dwarfs, we have direct evidence that the disk must be there. So it's common to see disks in white dwarfs, but not on neutron stars. And here we have the spectral energy distribution of you. I think this picture was shown before in previous presentations. And what we can see is that the infrared is this part here, and it's not a power law. So the disk is actually the thermal emission, like a black body or multi-temperature black body, is the best explanation for this. As I said, we don't see infrared in neutron stars. So we have about 2,000 isolated neutron stars known. Most of them are radio pulsars. And we have infrared confirmed in only 11 objects. This information was taken for this article from 2011, so it's like 10 years outdated. But I have searched for infrared counterparts this last decade, and the picture haven't changed that much. I have found like 3-4 objects apart from those 11 that have infrared detected, so it's still extremely rare. But when you talk about SGRA-XPs, the picture is different. We have 7 confirmed and 5 proposed infrared counterparts. So it's a class of less than 30 objects, and we have 12 objects with infrared among confirmed and candidates. It's a lot, especially when you think that we are saying 30 objects, but when we talk about confirmed magnetars, those that we have, for example, quiescent emission and not only outbursts that were never detected again, we have like about 23, 24 objects. So it's roughly half of the class has infrared. So why, in one hand, we have infrared emission being something really uncommon for neutron stars, but really common for SGRA-XPs. I think when you see this picture, it's something that really points out to white dwarfs, but I think this should be further studied, especially because one thing that I have been pointed out is that SGRA-XPs are really young objects, so the presence of the disk could be just a reflex of their age. And so here is the spectral energy distribution of the optical infrared emission in the Magnetar model, and they also use a disk to explain. So it's not something that is exclusive for our model. Actually, all models have a disk to explain the emission of this object specifically for you. Of course, when you talk about magnetars, the disk is not the only possible mechanism. There's people that argues that this infrared comes from a magnetospheric emission. And in this case, it can come from coherent plasma, cyclotron, or Couverture emission. And there are 2 classical approaches to see if they are disk emission, so in this case, a thermal emission, or if they are magnetospheric emission, which would be to search for pulsed or polarized emission in infrared. The problem is that depending on the results, in this case, if we don't find high polarization or high pulsed profile, pulsed fraction, we cannot distinguish between both of them, because high polarization, high pulsed fraction, we would only be expecting for magnetospheric emission. But if we found low polarization or pulsed fractions, these do not distinguish between both of them. And that's where we are right now. We don't have any, we have searched it for it, but we don't have, I'm not even gonna say that we don't have high polarization opposite fractions. We don't have polarization opposite fractions measured, only upper limits. So there's another possibility, which is looking for a correlation between the emission that we see in infrared and X-rays. And this was done before, so this specific picture that I'm showing here, oh, sorry. I've lost it where I was. Okay, I was here. So, sorry, I'm having problems. Okay, so the correlation was already searched for a few objects separately, not thinking about the whole class as a whole. And for some objects, they found a correlation. In this case, it's an object 1D2259, but for others, they don't find any type of correlation. So I've decided to do was to repeat this idea, but with more data. Not only one object, but all of them in the same picture, and considering soft and hard X-rays together. So I'm going to search for a correlation, not only about the soft X-rays, but soft plus hard X-rays and all objects. One thing that I'm going to say about this picture is that the upper picture is the X-rays and the lower pictures is infrared. So we can see there's only 4 measurements in infrared. And we see in both cases, this is an outburst of this object. We see a decay. So before showing the correlation, I'm going to show what the disk models expects. So the total flux would be the flux of the infrared emission, which will come from an irradiated disk, and the optical emission. In this case, of course, in infrared, we would only be seeing the disk. And the disk that we are going to use is this model, which is a multi-temperature. Hi?
It's 15 minutes, so you need to go fast, okay?
Okay. And so I'm gonna just put in here, and the correlation that we are expecting is 1.33, the X-rays. So this is the slope that if we put in a log. And what we find is this. First thing that we have to point out is that the correlation is there, the numbers are quite good. And the second thing is that the slope is pretty close to a disk. Another thing I have done, and this is actually bad for the idea of white dwarf, was to put in the same picture other classes of isolated neutron stars that has infrared. I haven't like redone the best fit. I have just put the objects in the previous picture, and we can see that we have in the black circles rotation power pulsars, and in the diamond is 1xt, and all of them seems to agree with this same slope. So not only we see a correlation for the infrared emission of SGRA-XPs, but the correlation seems to stand for other classes of neutron stars. This is not good for white dwarf models if you think just in the white infrared emission. And it's actually bad for the magnetospheric emission, because we don't expect to see a magnetospheric emission in a simple rotation power pulsar or in an XT. So the disk is the best explanation. And if we are seeing the disk, why this is so interesting? The first thing is because we can possibly find what is the origin of magnetars. So for example, we're talking about supernova, leftover of a supernova would be expecting a certain composition that could be found by James Webb, for example, if you do a spectroscopy. Also, if you like seeing magnetars being originated by merger, we would be expecting a different composition. And this merger idea gained attention the last couple of years because of the FRB-like events. There are a lot of models that explain the FRB-like events in magnetars that are originated by mergers. Also, it could have consequences on the evolution of magnetars. Of course, you are saying here, irradiated disks, they emit because of the debris, but if you're seeing the debris disks, probably there's gas, and the gas can have consequences on their evolution, for example, changing the spin down, and even emitting in X-rays because of accretion. So this is something that has to be taken into account when we're seeing disks too. And another thing that I think it's interesting, this could potentially explain the periodicity that we see in the FRBs. So this article shows that one specific extragalactic FRB has 16 days of a period. And there are several works, not only this one, but I have put this one specifically that shows that we could explain this periodicity by precession of a debris disk. So if we are really seeing infrared emission in SGR-XPs, and this infrared emission can be explained by disks, it could potentially explain the periodicity that we see in FRBs. And also there's this very unique object. I think it's one of the most interesting isolated neutron stars that we know right now. It's a CCO that is in the supernova remnant RCW103. It has magnetar-like activity and a period of 6.7 hours. So it's the slowest isolated neutron star node. The isolated neutron stars node that we have has 12 to 15 seconds of period, and this one has 6 hours. So one of the models to explain why it has such a slow period is because of the spin down caused by the disk. So if you're really seeing disks on isolated neutron stars and this specific object has infrared measured, this could explain why it has 6.7 hours. So it's really interesting to really understand what we are seeing in infrared, because it could have several consequences for other interesting properties that we see, not only on SGR AXPs, but also in other classes of isolated neutron stars. So I think I finished it. I probably taking more than my 15 minutes. So I think I'm just gonna wrap up here and see if anyone has any questions.
Thank you, Sarah, for your talk. Very good talk. And interesting this correlation to investigate more, in fact, and these infrared disks, maybe very few of them are in magnetars, but maybe they can split these two classes, maybe. Okay, good. So we don't have more time for questions because we are half an hour and you have still 3 to talk, only 15 minutes, 10 minutes maybe if they can. So next speaker now is Rafael, no, sorry, now is Manuel Felipe Souza from Instituto Nacional de Pesquisas Espaciais in Brazil. So
can you hear me?
Be fast as you can, okay?
Okay. Can you see my screen?
Yes, okay, perfect.
Okay. So, hello everyone. My name I'm Manuel Souza, and I'm a PhD student from National Institute for Space Research in Brazil. I would like to thank for the invitation and the opportunity to present my work. And today I'm going to talk about the gravitational wave, the production of gravitational wave, and the Dwarfs that have a rapid rotation. The motivation for doing this work comes from the observation of Dwarfs that have a rotation period of seconds to a few minutes, and from recent direct detection of gravitational wave made by LIGO and Virgo. The subjects raised this following question here. Could fast spin Dwarf emit gravitational waves with sufficient amplitudes to be detected by the proposed gravitational wave space mission? Seeking to answer this question, our aim in this study was to investigate two mechanisms of gravitational wave and fast spinning dwarfs. This mechanism were accretion of matter and magnetic deformation. We applied then this mechanism to 3 binary systems that have a fast spinning dwarf. It's then AR Quarry, AR Scarp, and RX G0648. It's important to mention here that for RX, there are some discussion about this compact star, because we don't know yet clearly if this compact star is a neutron star or a dwarf. Here in this work, we consider that this compact star is a dwarf. Okay, so let's see how we did the approach in its mechanism. The first mechanism that we will address here is accretion of matter. In this process, we consider that the dwarf is accreting matter via magnetic pole, or it has already accreted matter, forming a mountain of mass near these poles. We assume that the x of the magnetic pole does not coincide with the rotational x of the stars. With this configuration and this approach, and after some calculation, we can find these two equations here, one for luminosity and one for amplitude of the gravitational wave. This equation depends on some parameters like star radius, angular frequency, theta. Theta is the angle between the magnetic poles and the rotation x. They also depend on this parameter here, delta m. Delta m is the amount of mass accumulated in the magnetic poles. In general, it's difficult to measure or to observe this parameter, this quantity. So we infer some values to this quantity in order to calculate the luminosity and the amplitude. The results for the amplitude are presented here in this figure, where we use it the amplitude equation, this amplitude equation, and this parameter for the three-binary system to calculate the amplitude, assigning 4 values to delta m, to the accumulated mass. These values here are in the solar mass. After this estimate, we put these amplitudes on the sensitivity curve of the gravitational wave space detectors in order to see if these systems are detectable or not from this mechanism. So here we have the sensitivity curve for LISA, SIGO, and BBO, and the different values of delta m are displayed here from top to bottom, going from 10 to minus 3 solar mass to 10 to minus 6 solar mass. And what you can see about this figure, about this result, is the AE query and the RX are a good candidate to be detected by BBO and SIGO if they have an accumulated mass, or delta m, about of 10 to minus 5 solar mass or more. However, for the AR score, the gravitational radiation emitted from this mechanism would be hardly detected by the three-space instruments, because this system needs a large mountain of mass in its magnetic pole. Then the AR score is not a good candidate to be detected for this three-space instrument, considering this mechanism. Besides the analysis of the amplitude, we also analyze the energy emitted from the system by this mechanism. In other words, we calculated the efficiency here in relation to the spin down of the system. Okay, what we wanted to know here was how much the spin down luminosity is converted in gravitational waves for each delta m chosen. Here in this table, you have these results, where we can see here the efficiency values for these systems are so small. They are much less than 1. So we can conclude it from this outcome that the contribution of gravitational luminosity to spin down luminosity is negligible when we consider this mechanism. Therefore, the gravitational wave emission from this mechanism doesn't explain the rotational energy loss from the systems. Now, let's move on to the second mechanism, that is magnetic deformation. In this process, we consider that the generation of gravitational waves is due to the deformation of the white dwarf structure caused by its own intense magnetic field. Considering that the white dwarf is a triaxial, we can find these two equations here that depends on the magnetic field strength. However, we can also describe the amplitude as a function of the spin down. For example, here we have the amplitude that depends on the variation of the rotation frequency, and it also depends on this parameter here, eta. Eta here, again, is the efficiency of this process. From this parameter here,
Manuel, go to the results. Manuel, go to the results. Don't give details. Go to the results.
Okay. Okay. So we calculated the amplitudes from this equation here, assume some values to the efficiency here, going from 10 to -8 to 1 or 100%. Again, we put these amplitudes in the sensitivity curves of Lisa, BBO, and the cycle. And what we have is here in this figure. From this plot, we can observe that these equations are detectable with small values of efficiency. I mean, the system don't need to convert a large amount of rotational energy and gravitational wave in order to generate a detectable amplitude. However, it's interesting to know what is the magnetic field necessary to produce these amplitudes. Are the magnetic fields realistic or not? For doing this, we took the minimum efficiency detected by BBO here, these values, and we calculated the magnetic field strain. And for this outcome, we can observe that the magnetic field necessary are too intense, because this system are predicted to have magnetic field 2 orders of magnitude smaller when you consider the upper limits established by the canonical model of the Dwarf pulsars. Okay, so but one question may come to your head. What about this upper limits? If you took this upper limits, what are the gravitational wave amplitude generated by these magnetic fields? We did this calculation, and we find this value here. Here, for example, here we have the upper limit of the magnetic field strain, and we calculated from this values the amplitude and the efficiency. And you can see from these results that the amplitude and the efficiency are so small to be detected by the 3 space instruments. So the space detectors, the space instruments, will not be able to detect these systems when you consider these upper limits of the magnetic field strain. These systems require a magnetic field above 10 to 9 Gauss to be detected by BBO, for example. So these results and some others discussion can be found in this paper here that was published in January 2020. Before I almost finished my presentation, but before I finish my presentation, I take the opportunity to draw your guys' attention for this other paper here. In this study, we analyze the gravitational wave emission from a specific class of pulsars, soft gamma repeaters, anomalous X-ray pulsars. And in this study, we describe this object as a fat spinning Dwarf.
Thank you, Manuel, for your talk.
You use the magnetic information mechanism to do the analysis.
We don't have time for questions. Thanks for your talk, Manuel. Go to the next speaker now. Rafael de Lima, please.
Just a moment. Can you see my presentation?
Yes, if you can go fast to the results, please.
All right, good afternoon. I'm Rafael, and we'll be talking today about work on pulsar light curve analysis. We studied the thermal X-ray radiation that arises from a compacted object. a neutron star or white dwarf. Such a study can provide the properties of the star, mass and radius, the surface temperature, the size of the hotspots, and the magnetic field modulus. The radiation received actually arises in a very thin atmosphere, about 1 centimeter high. And the spectrum is determined by the magnetic field that can go from 10 to 9 Gauss to 10 to 14 Gauss if we consider magnetars. The atmosphere can be made of hydrogen, helium, carbon, oxygen, and so forth. And the opacities that determines the scattering process, the light will endure in the atmosphere. The radiation comes from a small portion of the star surface. Combining this with the stellar rotation, we have the lighthouse effect that generate this kind of sinusoidal pulse profile. But the flux, in many cases, doesn't drop to zero due to general relativistic effect. You can see here that appears the general relativistic effect in the end. This is the first ingredient of our model, the so-called Belobrod-Dobbs approximation. Here we have the star and the observer at the infinity. This is the line of sight here. And theta is the angle from where a photon arises. Notice that theta equals 0 at line of sight. The photon's path is curved due to space curvature, which we assume to be Schwarzschild type. And alpha is the angle the photon initially makes with the local surface normal. This is our ray tracing equation. F nu is the flux calculated by integrating the intensity at the specific frequency. This is this approximation here is good for radius greater than 3 Schwarzschild radius, and the error will be less than 3%. The problem to solve this equation is actually determine the integration region as Ni here. We use Tyroler's approach for effective area. The hotspots are finite in size, not points. And for each combination of mass and radius, we determine the maximal angle for integration. Here we see an example with 3 hotspots to different temperature, and this plane here marks the maximum visible surface. This would be here in the middle of for a normal star and not a compact star. These axes are our frame of reference. So here is the line of sight, the rotation axis, and the polar cap axis. Also, it's useful to define the angles. I is the angle between the line of sight and rotation axis, and J is the line, the angle between the rotation axis and the polar cap. Another ingredient is the beaming function, if I may. Of course, the amount of collimation we will have with this pulse will impact the flux we see. It could be isotropic or could be more collimated pulse. One possibility is the Hopf function studied by Dedel in 2001. This decreases the overall flux depending on the fluxes here, depending on alpha angle, which the photon arises. And here we see the phase diagram. The flux is normalized in order to compare different light curves for different visualization angles, each one of these. The maximal changes are about 13% comparing here with this one, which uses Hopf function. And to better understand this, we define the pulsed fraction is based on the difference of the mass flux and the minimum flux. Here we see the some of our own results for a fiducial neutron star of 1.4 solar masses and 12 kilometers. We are using magnetic field 2 times 10 to 10 Gauss. And here we have no beaming. These are the pulsed fractions mapped for all the combinations of angular visualization. So we can see the impact that the beaming have on the pulsed fractions we see here. Just a minute. Here I show a special white dwarf that we'll discuss it later. But notice that even white dwarf can have small values of pulsed fraction. We see here, and doesn't change a lot with the Hopf function, but changes the maximum here and here for these visualization angles. Also, accretion columns may have another kind of beaming, much more pronunciated. Here is the function, and we have 3 options for n equal 1, 2, or 3. 0 is the no beaming case. Here we have some of the results for the hardest beaming, n equals 3 for neutron star variables. The pulsed fractions could be 5 times bigger than the no beaming case. If we look here and this curve here, or go to 18 times bigger here and this one here. Sorry. Here. For white dwarf, the biggest change is the increasing of the 90% region. It has the maximum pulsed fraction. For the atmosphere, we use the pre-calculated tables provided by Ho through the XSpec routine, NS max G. These are for partial ionized hydrogen atmosphere and in the presence of different magnetic fields. Here I'm showing 10 to 10 Gauss and 10 to 11 Gauss. And here 10 to 12 Gauss and 10 to 13 Gauss. Due to the quality of these calculations, it's possible to interpolate between these tables and achieve different field models like 2 or 3, 10 to 12 Gauss. We can interpolate between this one. This is our first incursion on this type of fitting models. We used 2 data sets from the source, SGR J1745 pulsar. Here we show some results, the data and the theoretical curve for 2 epochs of were analyzed. At this time we still used black body radiation as our model. We have a third. We have 2 antibodal hotspots and 1 free hotspots to freely adjust. So these are the actual appearance of our results. The angles are showed for these 2 epochs, one for 2013 and 2016. We can see that hotspots changed their size from one epoch to the other. Here I show all the parameters, the entire set, and notice that the temperature of the two hot spots decreased from one epoch to the another. Here and this one here to decrease, but the third stayed almost at the same temperature.
Can you
yes
enlarge the picture, maybe Control Plus, because are too small. I don't know if you can.
Could you put in full screen?
I'm already at full screen. Let me try to increase
Control plus does not increase. No, okay, that's continue. Yes, now it's better.
Can you see now?
Yes, yes, now it's okay.
Yes, here is the increasing the temperature for these two hotspots, here and here. And this one stay almost at the same temperature. We think that the variation in sizes, as we saw here, the hotspots change its size, especially these antipodal hotspots, and the temperature, we saw that it dropped from one to the other. We think this could be interpreted as a result of the large thermal conductivity at the surface of the star. But notice that the third hotspot didn't change a lot its temperature. It may be the case because these spots merged, the south one and the third one. Okay, now it's working in progress now. We are testing these models with white dwarf parameters. Here we have some results for hydrogen atmosphere using beam, a high beam, n equals 2, which could be associated with the accretion columns on the star. I put it better here we can see the mass and the radius is the one I used previously to show the white dwarf parameters. And the magnetic field here is about 2 times 10 to 11 Gauss. This is for another, it's not the same white pulsar I used previously, is this one, J185246. Well, the conclusions, So we think that multiple polar magnetic fields are possible due to this strange arrangements that we got with the hotspots, and in some cases are the best way to fit well a pulse profile. We tested a lot with just 2 hotspots and antipodal, and we couldn't get a good result for this. The beaming effect obviously has a great impact on the theoretical pulsed fraction and must be taken into account when studying observations. Further studies are needed in order to better differentiate white dwarf and neutron stars, especially because they can have in some regions the same pulsed fraction. Okay, I thank a lot the Manuel and Giselle and all the organization for the invitation. Thank you very much.
Thank you, Rafael, for your talk. It's very interesting, these poles and these spots, more than one, and these multipolar magnetic fields seen as from your work. Very good. Thank you very much. So now the last speaker of the session, Silvia Nunes, is going to present her work about stability of massive hot white dwarfs.
So I would like to thank the organizers for the opportunity. My name is Silvia. I'm a PhD student of ITA in Brazil with my advisor, Professor Manuel Malheiro, and my co-advisor, Professor José Domingo. And today I'm going to talk about the massive hot white dwarfs, consequence of finite temperature in the structure and on the onset of instabilities. So our main motivation of this work are the very massive white dwarfs found in this work of Vance. And these massive white dwarfs are in the range of instabilities due to inverse beta decay, piconuclear reaction, and radial oscillation. And also in this limit is where general relativity effects are very important to describe the star. as pointed by Carvalho and collaborators. So in this work, we are going to study the structure of white dwarf with neat temperature in general relativity using a temperature distribution. We will analyze some very massive white dwarfs from this work and associate center temperatures, mass, radius according to their effective temperature and surface gravity. Also, we will investigate the fundamental frequencies of radial oscillation considering different center temperatures. And we will analyze the effects of temperature in the onset of instabilities. Also, we will create an equation that relates mass with effective temperature and gravity. So here's the equation of state we are using. So the pressure has contribution from electrons, nucleons, photons, and lattice. In the core, and also the energy density. In the core, we consider a constant temperature, and the envelope, we consider a temperature distribution. We use these three works to determine the equation of state. And here is the equation of state, the pressure as a function of the energy density to central temperatures from 10 to the 4th to 10 to the 8th. This is a result that was obtained before, but as we consider temperature distribution, our results are different from the others. And the nucleus pressure, we found that are very important in this region. So for the structure, we consider the Thoma-Oppenheim-Volkoff equation to describe the star. And here we are showing a massive white dwarf with masses of 1.37 solar masses. Here's the mass as a function of radial coordinate to central temperatures from 10 to the 4th to 10 to the 8th Kelvin. What we can notice here is that the mass increased with the radial coordinate, and for central temperatures above 5 times 10 to the 7, we can note that the radius is increased by central temperature. And comparing 10 to the 4 to 10 to the 8, we found that the radius increased around 135%. And this is mainly an effect of nucleus pressure, and it's very comparable to what we expected from the evolution of a white dwarf, because when a white dwarf cools, it shrinks. So here we presented several stars. So here is mass as a function of central energy density for 10 to the 4 to 10 to the 8 Kelvin. What we can notice that our curves have a shift upward here in this region, something that wasn't obtained before. These pink dots represents the turning point, and we found that they coincided to the onset of instabilities due to radial oscillations. This region that we cut is where the non-degenerate equation of state begins to the core. So the star here, the curves here diverge, so are unstable, so we cut it. And here is our curves comparing to observational data. Here's mass as a function of radius from 10 to the 4 to 10 to the 8 Kelvin. The observable white dwarfs we represent here are from these works. So what we can notice here, the pink dots are also the turning point. What we can notice here is that most of the white dwarfs are in the range of central temperature below 5 times 10 to the 7 Kelvin, and in the range of mass from 0.3 to 1.3, so here. But there are some very massive white dwarfs that coincide with our high central temperature curves. So these white dwarfs are the one that we are going to analyze later. So here's the mass as a function of surface gravity for the same central temperatures. Most of white dwarfs are located here, and within the surface gravity from 10 to the 7 to 10 to the 9 centimeters per second square. And the most massive white dwarfs are here with surface gravity above 10 to the 9 centimeter per second square. So here the pink dots also represent the turning point and the onset of radial oscillation. And we are going to analyze some of these white dwarfs. So for our curves, we obtain the mass, radius, surface gravity, and effective temperature according to a central temperature and an energy density. So what we do is use the effective temperature and gravity that when is reported for some observable white dwarfs, in our model to get mass, radius, and center temperature. Once we fit the center temperature, we're going to use this formula from Crust and put the center temperature here to look for the alpha constant. The alpha constant in this work of Crust is 2.56. So we are going to compare the results with this equation, but we don't use this equation to estimate the center temperature. So here is what was reported by Vance in the left side. So here's the effective temperature, surface gravity. They use a fit to determine the mass and radius. And here's what we obtained: the mass, radius, center temperature, and alpha. So what we can notice here is that we found very similar values of mass and radius comparing to Vance, with exception of this white dwarf.
Sylvia, if you maybe you can do Control plus to enlarge a little bit. I don't know. Yes, good.
With the exception of this white dwarf, that we found a smaller mass value than the one that Vance reported. And another thing that we have to look is the alpha constant that we found 2.48, a very close value to the one that Crust found. And here we use an envelope of helium. So using an envelope of hydrogen and helium, we also made a comparison to Vance values. We found very close results to mass and radius, with the exception of this white dwarf that we found a smaller value than the reported by Vance. Oh, something I forgot. The center temperature we found are, all the center temperatures we found are above 10 to the 7, but this reaches 9 times 10 to the 7, a very high center temperature. So here also all the center temperatures are above 10 to the 7. And what we found for the alpha parameter, alpha constant, is 2.54, a closest value to what Crust found. So now we're going to analyze these white dwarfs that we found smaller masses than the one that Vance obtained. So these two are what Vance obtained, and these two are what we obtain. So these are the corresponding with the colors. So what we have noticed is that when you consider general relativity, if you maintain the surface gravity constant, the results from general relativity are smaller mass than the ones that you obtain with the Newtonian framework. So what we see here, it's a consequence of we consider general relativity, and they use an evolution code to get the mass and radius. So what I was talking about is that when you fix the gravity, if the radius is smaller for GR, you get smaller masses than the ones that you find for Newtonian case. So what we do next is to find an equation of mass that once you have the effective temperature and the gravity, and also this alpha constant, depending on the atmosphere composition.
Enlarge, please, enlarge.
Wait. Once you have the alpha constant.
Aumenta.
Once you have the effective temperature and gravity, you have the alpha constant according to our calculations of the atmosphere composition, you have the center temperature. So having the center temperature,
yes, okay, good.
You find these K constants according to the center temperature. If you reach a center temperature that's not here, you can do an interpolation. So with this case that depends on the center temperature, you use this equation. So here is K0, K1, K2, K3, and gravity that you already have. So you can get a mass equation with gravity and effective temperature. So this is also a novel result. So we also done an instability study. So using Chandrasekhar equation, we found the fundamental weighted frequencies of radial oscillation So here's the omega square, this is the frequency of radial oscillation as a function of the central energy density to central temperature 10 to the 4 to 10 to the 8 Kelvin. So what we have noticed is that this low temperature curve that we obtained is the same one that was found by Wheeler, Hansen, and Cox, and Shammungan for temperatures, for zero temperatures, to completely degenerate stars. Here, if we see for omega square equal to 0 is the above omega square equal to 0, we have stability sequence, and below we have instability sequence. What we can see, we can notice here is that the curves have a different down to when we increase the central temperature. And when we increase the central temperature, the threshold density where instability occurs are smaller than the ones for low temperature star. So now we show the omega square as a function of the mass. So the same behavior, the omega square has a maximum, then decrease. For omega square above 0, we have stable configurations. And here we can notice that most of the stars with 0.3 to 1.3 solar masses are in this range. So these stars are associated with AJ frequencies from 0 to 4.5. And with our fitting, we also returned the AJ frequencies of the massive observable stars that are in the range of 2.8 to 4.6. So we found that observable stars have very low omega square values. So we are finishing our stability study. Here is the mass as a function of central energy density to 10 to the 4th Kelvin to 10 to the 8th, the same central temperatures as before. So what we can notice here are the pink dots represents the turning point and also coincides to the onset of instabilities due to radial oscillation. What we have noticed here is that for low temperature stars, the piconuclear reactions are the one that rule the instability, as we already know. But when we consider stars with central temperatures near 10 to the 8th Kelvin, the radial oscillations are very important to describe the stability of a star. So we found the structure and stability of white dwarf near temperature, that stars near maximum mass are affected by nucleus pressure. We found mass, radius, and central temperatures according to the effective temperature and gravity of observable white dwarfs with surface gravity above this limit. Another equation for astronomers to determine the massive white dwarf mass according to GR, and the onset of instabilities due to radial oscillation is important to the central temperatures around 10 to the 8th Kelvin. So that's it. Thank you.
Thank you, Sylvia, very much for your talk. This equation you obtain is only for stars with G above 10 to 9, yes?
Yes, it's only for massive stars.
Okay, good. So, guys, thanks for all of you. We are just in 2 minutes, they are going to shut down the session. So it's why I was worried. Okay, so thank you very much for all of your talks, your participation in NG16, and with excellent talks, okay? And so I think I will give a, sorry, here my phone, yeah. So I give a farewell for all of you, okay? If you want to open your cameras, you can do it now, and we say goodbye, okay, for all of you.
Thank you, Manuel.
Thank you. If you can open your microphones, thanks a lot for all of you. I think it was a very good session.
Thank you.
You can use the emails from the others to maintain contact, okay? And send me your talks PDF talks by email, okay, if you can, okay? Because in that case, I can put all together if the organization asks me, I don't know. Okay, so Bani, Manuel, Silvia, Jaziel, Cláudia, Sara, Rafael, Surati.
Thank you very much.
Arbanil.
Thank you very much. I love you.
And have a nice surviving from COVID. COVID. Okay. Ciao. Bye.
Bye bye.
Thanks a lot.
Bye.
Thanks a lot.
Bye bye.